To start off, we're going to talk about the history and standards of the Linux operating system. So Linux is a member of Unix family of operating systems. Well, in computing terms, Unix has a long history. One of the notable features of the Unix system is that its development was not controlled by a single vendor or organization. Rather, many groups, both commercial and non-commercial, contributed to its evolution. Now, this history resulted in many innovative features being added to Unix, but everything has a drawback as well. So that is why it also had the negative consequences that Unix implementation diverged over time. So a problem emerged that writing applications that worked on all Unix implementations became increasingly difficult. Now this was the factor that led to a drive for the standardization of Unix implementation. Between 1969 and 1979, Unix went through a number of releases. However, even with these 6 additions, a standard was not accepted by the community or by the Linux community. So let's just simply talk about Linux. The term Linux is commonly used to refer to the entire Unix-like operating system, and Linux kernel is a part of Unix operating system. So let's talk about standardization. By the late 1980s, the wide variety of available Unix implementations also had its drawbacks. Now, some of these Unix implementations were based on BSD, others were based on System V, and some drew features from both the variants. Furthermore, each commercial vendor had added extra features to its own implementation. The consequence was that moving software and people from the Unix implementation to another became steadily more and more difficult. This situation created a strong pressure for the standardization of the C programming language and the Unix system, so that applications could more easily be ported from one system to another. So after the standardization, C became the programming language for Linux and Unix operating systems. Important concept that we are going to work with during this course. So to understand the kernel, we are going to talk about the operating system and how do we perceive the operating system. Well, the term operating system is commonly used with two different meanings. First off, we use it to denote the entire package consisting of the central software managing a computer's resource and all of the accompanying standard software tools, such as we can say command line interpreters, graphical user interfaces, file utilities, and much more. Secondly, or more precisely, we use the term operating system to refer to the central software that manages and allocates computer resources. Now these resources can be RAM, CPU, and all the devices connecting to the CPU. So the term kernel is often used as a synonym for the second meaning, which is why the kernel is called the core operating system. It is possible to run programs without a computer kernel. However, the presence of a kernel greatly simplifies the writing and use of other programs and increases the power and flexibility which is available to the programmer. Now you may ask, what are the tasks performed by the kernel? Well, we have some major tasks listed over here, which are process scheduling, memory management, provision of the file system, creating and termination of processes, access to devices, networking, provision of a system call API, and so much more. So if you were to talk about these tasks or define them, it would take a lot of time. We will go through them during this course. So next up we have an important difference. What is a kernel mode versus the user mode? So you should know that modern processor architecture typically allows the CPU to operate in at least two different modes. We have the user mode and then the kernel mode. Also, the kernel mode is sometimes referred to as the supervisor mode. So when running in user mode, the CPU can access only memory that is marked as being in user space. And when it tries to or when it attempts to access memory which is located in the kernel space, it results in a hardware exception. And when we are running in the kernel mode, the CPU can access both user and kernel memory space. So what do we mean by this? So if a program is running in the user mode, it does not have all the privileges to work with. But if a program is given superuser right or supervisor rights, I should say, then the program has much more rights, or I should say administrative level rights, because in Windows we have something called the administrator rights, and in Linux we have the superuser rights, and then we have the supervisor rights. So these are all different, but just wrap your head around this idea that the kernel mode offers more rights to a process. And then we have process versus the kernel views of the system. So a running system typically has numerous processes. For example, Many things happen asynchronously. An executing program does not know when it will next time out, which other process will then be scheduled for the CPU and in what order, or when it will be next scheduled. The delivery of signals and the occurrence of inter-process communication events are mediated by the kernel and can occur at any time for a process. We can even say that many things happen transparently for a process. And on the other hand, a running system has only one kernel that knows and controls everything. A kernel is like a manager. The kernel facilitates the running of all processes on the system. The kernel decides which process will next obtain access to the CPU, when it will do so, and for how long. The way processes execute is that the CPU is given to a process for a particular amount of time, and then the CPU is rescheduled to some other process. Now this whole management is done by the kernel. The kernel maintains data structures containing information about all running processes and updates these structures as processes are created or when the processes change their state and even when the process terminates. So that was it for the kernel. Now by now you may have an idea what a kernel is. It is like a secret agent which controls everything. So next up we have the shell. Now if you have seen the videos of Linux, then you know that we have a shell which is used to read commands typed by a user and execute appropriate programs in response to those commands. Now such a program which reads the user commands and executes the command or responses it by a process is oftentimes known as a command interpreter. So the shell is a command interpreter. There are multiple types of shell present in the Linux operating system, and there are multiple names or terms used for the shell. We have the term login shell, which is used to denote the process that is created to run a shell when the user first logs in. And then there are multiple different shells which can often work with different users and which can even be present for a particular user on the computer machine. Now if you talk about number of important shells that have appeared over the time, we have the Bourne shell, which is the oldest and the widely used shell. This was written by Steve Bourne and it was the standard for the shell for the 7th edition of Unix. Then we have the C shell. This shell was written by Bill Joy at the University of California at Berkeley. It was given the name of C shell because of its resemblance of many of the flow control constructs of this shell to those of the C programming language. Then we even have the Korn shell. This shell was written as the successor to the Bourne shell by David Korn at AT&T Bell Laboratories. And then lastly, we have the most famous and the most widely used shell of the current time, which is the Born Again shell. This is also known as the Bash shell. This shell is the GNU project re-implementation of the Bourne shell. It supplies interactive features similar to those available in the C and the Korn shell. The shells are designed not merely for interactive use but also for the interpretation of shell scripts, which are text files containing shell commands. I am pretty sure that you came here for learning system programming in Linux, then you have seen some videos on YouTube and you have seen the working of shell commands, even if you were not familiar with them. Now there are multiple shells available on the market that you can install in your operating system, but you should know that each of the shell performs almost similar tasks. So throughout this course, we will be referring to the shell with the understanding that all the shells are operating in the same manner. Each user on the system is uniquely identified, and users may belong to groups. So let's talk about users. Every user of the system has a unique login name, which is known as the username, and a corresponding numeric user ID. For each user, they are defined by a line in the system password file. Now this password file can be found through the path /etc/password. Now this file also includes the following additional information. So first off, we have the group ID, the numeric group ID of the first of the groups of which the user is a member of. Next up, we have the home directory, the initial directory into which the user is placed after logging in. Then we have the login shell, the name of the program to be executed to interpret user commands. Now we have talked about the shells and the login shells in the previous video. Now you may be wondering, where is the password? The password record may also include the user's password in encrypted form. However, for security reasons, the password is often stored in a separate shadow password file which is hidden from the user. Now this file is only readable to privileged users. Next up, let's talk about groups. For administrative purposes in particular, or for controlling access to files and other system resources, it is useful to organize users into groups. For example, the people in a team working on a single project and thus sharing a common set of files might all be made members of the same group. In early Unix implementations, a user could be a member of only one group, but BSD allowed a user to simultaneously belong to multiple groups, an idea that was taken up by other Unix implementations. Each group is identified by a single line in the system group file, which path is /etc/group. Now this file, just like the password file, contains some additional information which are as the group name, which is the unique name of the group, the group ID, which is the numeric ID associated with this group, user list, a comma-separated list of login names of users who are members of this group. Now lastly, we have the superusers. One user, which is known as the superusers, has special privileges within the system. The superuser account has user ID 0 and normally has the login name root. On typical Unix systems, the superuser bypasses all permission checks in the system. Thus, for example, the superuser can access any file in the system regardless of the permission on that file and can send signals to any user process in the system. The system administrator uses the superuser account to perform various administrative tasks on the system. Let's talk about the directories, links, and files in the Linux operating system. The kernel maintains a single hierarchical directory structure to organize all files in the system. This is different from various operating systems such as the Microsoft Windows, where each disk device has its own directory hierarchy. At the base of this hierarchy is the root directory, which is named as the slash. Now you can look at this figure and you will notice the backslash is the root of all the hierarchy. We have some rounded rectangles and some square corner rectangles. Now these rounded rectangles are directories or folders, and the square corner rectangles are files. Remember that all files and directories are children or further removed descendants of the root directory, which is the slash. So let's talk about file types. Each file is marked with a type indicating what kind of file it is. One of these file types denotes ordinary data file, which are usually called regular or plain files to distinguish them from other file types. These other file types include devices, pipes, sockets, directories, and symbolic links. So what are directories and links? A directory is a special file whose content take the form of a table of file names coupled with reference to the corresponding file. This file name plus reference association is called a link. Files may have multiple links and these multiple names in the same or in different directories. But what is the difference between a link and a symbolic link? A symbolic link provides an alternative name for a file, where a normal link is a file plus pointer entry in the directory list. A symbolic link is a specially marked file containing the name of another file. So now let's talk about file names. We all know what file names are. On most Linux systems, file names can be up to 255 characters long and can contain characters other than the slashes and null character, which is the \0. Now let's talk about path name in Linux operating system. A path name is a string consisting of an optional initial slash followed by a series of file names separated by slashes. A path name is read from left to right. Each file name resides in the directory specified by the preceding part of the path name. Now there is a thing called as absolute path name. So an absolute path name begins with a slash and specifies the location of a file with respect to the root directory. And then there is the relative path name, which specifies the location of the file relative to a process's current working directory and is distinguished from an absolute path name by the absence of an initial slash. Since we have already mentioned the relative path name, let's talk about the current working directory. So each process has a current working directory. This is the process's current location within the single hierarchy, and it is from this directory that relative path names are interpreted for the process. And lastly, we have the file ownership and permissions. Each file name has an associated user ID and a group ID that defines the owner of the file and the group which it belongs. The ownership of a file is used to determine which writes are available to which users. So let's talk about the I/O model or the file I/O model. One of the distinguishing features of the I/O model on Unix operating system is the concept of universality of input and output devices or input and output operations. This means that the same system call such as open, read, write, close or whatever are used to perform input and output on all types of files, including devices. Thus, a program employing these system calls will work on any type of file. Now, this concept is prominently different from other operating systems. Now, if we talk about the kernel essentially provides one file type, which is a sequential stream of bytes, which in the case of disk files, disks, and tape devices can be randomly accessed using the lseek system call. Then we have a thing called file descriptors. The I/O system calls refer to open files using a file descriptor. A file descriptor is usually a small non-negative integer value. A file descriptor is typically obtained by a call to open function, which takes a path name argument specifying a file upon which I/O operation is to be performed. And then lastly we have the stdio library, which is the standard input-output library. And if we work in the C programming language, we always include this library, which is the stdio.h header file, to make sure that we can use all of the system calls which are related to input-output operations. Now this header file or this library includes multiple functions which help us perform I/O system calls or I/O operations in the Linux operating system. Let's talk about programs. Programs normally exist in two forms. The first form is the source code, which is a human readable text consisting of a series of statements written in a programming language, which in case of Linux is the C programming language. Now to be executed, source code must be converted to the second form, which is the binary machine language instruction that the computer can understand. The two meanings of the term program are normally considered synonyms, since the step of compiling and linking converts source code into semantical equivalent of binary machine code. When talking about programs, we should also talk about filters. A filter is a name often applied to a program that reads its input from the standard input, which is the stdin, performs some transformation of that input, and writes the transformed data to stdout, which is the standard output. Examples of filters include cat, grep, tr, sort, wc, and so on. You may not have an idea of what these commands are, but we will cover them in this course. Next up, we have the command line arguments. In C programming language, programs can access the command line arguments, the words that are supplied on the command when the program is about to run. To access the command line arguments, the main function of the program is declared as the following. So we have the main function with its data type can be integer, can be void, and within the round parentheses we pass on these two parameters. First off is the integer argument C, which counts the number of total arguments, or we should say the number of command line arguments passed to the program. And then we have a character array called the argv, which includes all the actual command lines arguments. Now in this character array, which is the argv, the first index or the 0th index contains the actual name of the program itself. So if we want to work with command line arguments, we should keep this in mind that we have to ignore the first index of this argv array. So let's talk about process. Well, a process is an instance of an executing program. We can say that when a program is executed, the kernel loads the code of the program into the virtual memory, allocates space for the program variables, and sets up the kernel bookkeeping data structure to record various information. Now this information contains the process ID, termination status, user IDs, and group IDs about the process. From a kernel point of view, processes are the entities among which the kernel must share the various resources of the computer. But there are some resources that are limited, such as the memory. So in that case, the kernel initially allocates some amount of that resource, which in our case is the memory, to the process and adjusts this allocation over the lifetime of the process in response to the demands of the process. And when a process terminates, which is called the process termination, all such resources are released for reuse by other processes. A process is logically divided into the following parts, which are known as segments, and this all can be labeled as the process memory layout. So we have the first segment, which is the text, which are the instructions of the program. Then we have the data, which are the static variables used by the program. And then we have the heap. Heap is an area from which programs can dynamically allocate extra memory. And the last segment of a process is the stack. A stack is a piece of memory that grows and shrinks as functions are called and returned. And a stack is used to allocate storage for local variables and function called linkage information. A process can create new processes using the fork system call. The process that calls the fork is referred to as the parent process, and the process that is created as the result of that fork call is known as the child process. Then we have a thing called process ID. So each process has a unique integer process identifier, which is known as its process ID, and each process has a parent process identifier as well. Now if we talk about the termination of a process can terminate in one of two ways. Number one is by requesting its own termination by using the exit system call, and the second way is by being killed by the delivery of a signal. Now there is one thing that we must know, and that is the init process. So when booting the system, the kernel creates a special process which is known as the init. Now the init has the aka parent of all processes. Now why is that so? Well, that is because that all the processes on the system are created using the fork call by either the init process or by the descendants of the init process, thus creating a tree with init process at its root. And that is why we have the term parent of all processes. Then we have another type of process, which is the daemon process. A daemon process is a special purpose process that is created and handled by the system in the same way as other processes. But the only difference the daemon process has with the other processes is that it is distinguished by the following characteristics. Now these characteristics are, the first and the foremost, that it is a very long-lived process. A daemon process is often started at system boot and remains in existence until the system is about to shut down. And the second main characteristic is that it runs in the background and has no controlling terminal from which it can read input or to which it can write output. One of the last and the most important fundamental concepts of Linux operating system is the inter-process communication and the synchronization. So if we talk about the IPC, which is known as the inter-process communication, a running Linux system consists of numerous processes, many of which operate independently of each other. However, some processes cooperate to achieve their intended purposes, and these processes need the method of communicating with one another and synchronizing their actions. Just like we work in a team, we need to communicate with each other. Now, just like we write text messages to communicate with each other, processes also communicate, or I should say, one of the methods through which processes communicate with each other is through writing data or writing and reading information from the disk file. This method of communication is very slow and inflexible. So that is why all the new modern Unix implementations have a rich set of mechanisms for inter-process communications. Now, some of these mechanisms include signals, which are used to indicate that an event has occurred, pipes, which can be used to transfer data between processes. Then we have sockets, which can be used to transfer data from one process to another, either both of the processes existing on the same computer or even different computers connected by the network. Then we have other things like file locking, message queues, semaphores, shared memory, and so on. In the last video, we discussed our mechanism for the IPC, or the inter-process communication, which were the signals. So let's talk about signals. Signals are often described as software interrupts. The arrival of a signal informs a process that some event has occurred or some exceptional condition has occurred. Now there are various types of signals, each of which identifies a different event or condition. But there is one thing in common, that each signal type is identified by an integer, although every signal has different integers. And these signals are defined with the symbolic names of the form sig, sig, and then you have the 4 x's, which can be used to fill in the type of the sig or the signal. The signals can be sent to a process by the process itself or by the kernel or even by some other process. And for the example of signals, we can say that the kernel may send a signal to a process when one of the following events occur, such as the user types the interrupt character, which in Linux operating system is the Ctrl+C command on the keyboard, or one of the process's child has terminated, then the parent process gets a signal that his children has died or completed its process, or when the timer set by a process has expired, or even when the process attempted to access an invalid memory address, it gets a signal. So that is how you do inter-process communication even with the kernel, through signals. Let's talk about user mode and kernel mode, or I should say the user space versus the kernel space, in a little more detail. So the main feature of the Linux operating system is to provide security and accessibility to the underlying hardware. Now what do I mean by this? So you basically don't want a program or any application software to mess with your hardware. For example, if you get a virus or any spamware or malware and it has access to the hardware, it can really screw up your PC. So that is why there is something called kernel. We have already discussed what a kernel is and what it does, so I'm not going to go into that thing. But there are some processes that do need some kind of hardware control. Like if you want to take some inputs from the user, then you need to work with IO devices or IO operations. So how do you get that, or how does that program or how does that process get that thing? So if you look at this figure right over here, you see that there are three layers. The first one is the user mode, which is also known as the user space. This is the layer where most of the user applications are working. And then in the middle we have the kernel mode. Now this is the layer where the kernel is residing. And lastly we have the hardware. The hardware contains CPU, memory, IO devices, and so on. So whenever a program wants to use some kind of hardware, it actually requests the kernel to move the process to the kernel space. What the kernel does, it asks the program what are his requirements. After knowing the requirements, the kernel moves that particular program to the kernel space where it has privileged access. Now what do I mean by this? All the programs which are running or executing in the user space have a very limited amount of rights. But in the kernel space, all the programs get privileged rights. So that is how whenever a program or whenever a user application moves to the kernel space, it has the access to the IO devices. A user program says to the kernel that I want hardware. The kernel says, yeah, you can use the hardware, but you need to use system calls. The system calls are a way of accessing the underlying hardware, and the kernel becomes a middleman between the hardware and the user program. So that was the difference between a user mode versus the kernel mode and how user applications work with privileged rights. Now let's talk about library functions and the execution of C programs in Linux operating system. Because throughout this course, we would be working with system programming in Linux using the C programming language. So let's first talk about the library functions. Well, a library function is simply one of the multitude of functions that constitutes the standard C library. Generally, the standard C library is placed under the header file libc.h, but you do not have to include that every time you want to work with standard C library functions. There are different implementations of the standard C library on the various Unix implementations, but the most commonly used implementation on Linux is the GNU C library, which is also known as glibc. Now this library contains multiple functions, some of them which do not use the system calls. For example, we have functions for string manipulations. On the other hand, we have some library functions which are layered on top of system calls. For example, we have a function in C programming language which is the fopen function to open up a file. Now this fopen function works on any operating system, but on the back end it is based on the system call open function, or I should simply say system call open. To compile programs in the Linux operating system, open up any folder, open up a terminal, you need to make sure that you have a GCC installed. For that, just simply search for GCC --version. If you do not have the GCC installed, then you can download the GCC using the following command, which is the sudo apt-get install build essentials. I have already installed it, but in case you do not have the GCC compiler or anything missing, then you have to simply write down this command in the terminal and execute it. Then you want to create a new file, a C programming file. So you can do that by using touch, and let's name it demo.c. Make sure the extension is C because we're working with the C programming language. Then you can open it up in any text editor or any code editor as well. I am assuming that you know how to work with the C programming language since you have opted out for this course of system programming in Linux. So I've written down a very basic hello world program, but I've changed the hello world to hello programmers. So to execute this program, first save the file and quit the text editor. Open up the terminal So to compile it, you use the command gcc, then the source code or the source file, which is demo.c, then you put a -o, or some people call it -o, and then the object file, which is going to be demo. Once the compilation is done, you can execute the file using the following command, which is the // and then the object file. And just like that, we have the output on our screens. So that is how you work with library functions, as printf was a standard C library function which is used to print output to the screen or to the terminal. So now you have an idea of how to compile C programs and how to execute them in the Linux operating system. During this course, we might opt out for a VS Code editor just to use its snippets. Okay, we have mentioned system calls quite a lot of times in this course, even though it's just the start. So what are system calls? A system call is a controlled entry point into the kernel, allowing a process to request that the kernel perform some action on the process's behalf. Just in the previous example, we used a function called printf that was actually using a system call which was write. Now the process was asking the kernel to write on the behalf of the process. Now the kernel makes a range of services accessible to the programs via the system call application programming interface. Now if you have a programming background, you might know what an API is. So system calls are basically APIs. Now the services accessible to the program through the system call API include creating a new process, performing IO operations, creating pipes for inter-process communications, and so on. System call changes the processor state from the user mode to the kernel mode, and we already know what is the difference between the user space and the kernel space. It does that so that the CPU can access protected kernel memory. So from a programming point of view, invoking a system call is very similar to invoking a normal function or normal standard C functions. So let's use a system call. Let's simply create a new file. Let's call it systemcall1, or let's call it syscall.c. Previously, we have used a function from the standard C library, which was the printf function, to print a string to the screen or to the terminal. But this time we are going to use the write system call. So to use the write system call, you need to include the following library, which is the unistd.h. So in this very basic program, we have created a buffer array. We have passed in some string value to that array, and we're using the write function or the write system call to print it to the terminal. Okay, so the last thing that you need to do is to include the library, which is the string.h, and you need to change this variable to length. After that, you know what you need to do. You need to open up a terminal, use the GCC compiler to compile this program, and you have to run this program using the following command. And there you go. So that is our string, which has been successfully printed to the terminal. And now we know that we did not use the standard C library functions, but instead we use a system call. So now we have executed a system call using the C programming language. Now let's take a little more detailed look on the working of system calls. So you have this figure on your screen, and as you can see, we have two different modes, user mode and the kernel mode. And in the user mode, we have the application program and a glibc wrapper function. And in the kernel mode, we have a trap handler and a system call service routine. So if you look closely in the application program, we have a system call which is the exec ve. Now this system call is actually used to execute the program which is pointed by the path. So what happens is that whenever this application program reaches a system call, it passes it to the wrapper function. The wrapper function must make all of the system call arguments available to the system call trap handling routine. Now since all the system calls enter the kernel in the same way, the kernel needs some method of identifying the system call. To permit this, the wrapper function copies the system call number, which is unique, into the specific CPU register. So that was the working of the wrapper function. Now you should know that every system call has a unique number because the CPU or the kernel cannot differentiate between the names of the system calls. So it does so by using the wrapper function, and wrapper function actually does so using the number of the system call or the value of the system call. Now when the wrapper function places the system call number into the CPU register, the mode changes from the user mode to the kernel mode, and then we enter the trap handler. Now the trap handler is actually keeping a table of system calls, and it looks for the specific number that is present in the CPU register. Upon finding the number, it goes into the system call service routine and executes that specific system call. Upon success or even upon the error, the control passes back to the trap handler, which either raises an interrupt handler in case of error, or in case of success, the control flows back to the user mode inside the wrapper function. If it's a success, then the control goes back to the user application or the application program. So that was the working of system calls and how it interacts with the hardware or how it interacts with the kernel mode. So in this section, we are going to talk about files input-output operations or working with files in general. So in Linux operating system, every file has three permissions. We have the read permission, write permission, and similarly we have the execute permission. Now I am assuming that you know what a file is because I've already explained it in the fundamental concepts, and you have probably worked with files on Windows operating system or any other operating system. Now each file has some value, and this value denotes the permissions. For example, if a file has a value of 4, that means that this is readable. Now this value is calculated by giving the permission some values. So the read has the value 4, write has the value 2, and execute has the value 1. Now remember that every file in the Linux operating system can be accessed by different users. And the different users on a Linux operating system are the users, we have groups, and then we have others. Now if we look at the details of a file, in Linux operating system, everything is considered to be a file. Now what do I mean by this? So if we open up the properties of a file, and if that file starts with a hyphen, then that means that that particular file is a regular file, which is also known as a data file. But in case that file starts with a character D, this would mean that that file is not a regular file, rather a directory or a path. Similarly, we have the prefix C, which stands for character device file, and then we have the prefix B, S, P, and I for block device, local socket file, named pipe, and symbolic link. Now if we open up a folder, I'm going to use this folder which I have used to create some basic C programs. And if I open up a terminal inside this folder, so there is this command which is ls space -al. Now this command is used to show all the files in a particular folder or in a particular directory, and it shows its detail as well. Let me bring the terminal to the middle of the screen. Now if you see, we have a file named demo. Now if you remember, this was the first C program that we created. Now if you look over here to the very left of it, you see that there's a prefix hyphen. Now this means that this is a regular or a data file. And then we had rwx, rwx, and rwx. What is this gibberish? Every file has three permissions: read, write, and execute, and X stands for execute, by the way. And every file has three different types of users. So that is why we have three sets of read, write, executable permissions. And if we look over here, we have a file which is named as a single dot. Now this is not actually a file. I mean, this is a file according to Linux operating system, but if you are coming from any other operating system, this would be a link to go back to the previous directory. Similarly, the double dot is a link to go back to the home directory. So the prefix is D for these types of files. Anyways, if you look at this, we have a file named open basics. Now it has read, write, executable permissions for the user, read, write, executable permissions for the groups, and read and execute permissions for others, and not write permissions for others. So why are permissions necessary? Well, if you're working with a C program and you're trying to write an application that is going to be working with different files, and you try to access a file in a read-only mode and that file does not even have read-only permissions, then you'll simply get an error. So you need to make sure that you're working with the correct files with the correct permissions. So how do you change the permissions of a file? Well, we have a command in Linux which is the chmod, and then you have to type in some value, which is an integer value, which looks something like this, 777, and then we have the name of the file. So let's do open basics. Let's again view all the list, and if you look at it, this time around I have given every permission to every user. Now what was this 777? I've already told you that read has the value 4, write has the value 2, and executable has the value 7. So the first character defines the permissions for the users, the second character defines permissions for the groups, the third character defines permissions for the others. And you calculate this value by adding the values of the permissions that you want to give to the file. For example, if I want to give only executable permissions to the users, then I will use something like chmod 177. And in case I want to give the permissions of read write executable to the user and I don't want to give any permission to groups or others, then I would simply use something like 700 and then the name of the file. Now this is going to be very important, not this particular command but the concept of permissions, because in this whole section we are going to be working with files and we are going to be reading them in read-only mode or opening them in read-only mode, writing to them and closing them. So we would need some permissions. So that is why this concept is very important. So let's talk about the file descriptor. So all the system calls that are being performed always refer to the open file descriptor. Now this file descriptor is denoted by FD conventionally, not mandatorily. And this file descriptor is usually a very small or small non-negative integer value. File descriptors are used to refer to all types of files, or I should say all types of open files, including pipes, FIFOs, sockets, terminals, devices, and even regular files. Now you should know that every process has its own set of file descriptors. Almost every program uses or is expected to use the 3 standard file descriptors. Now these 3 file descriptors are opened on the program's behalf by the shell. And the interesting thing is that the file descriptors are opened even before the program actually starts. Now you can see the 3 file descriptors on your screen with the values 0, 1 and 2. 0 being the standard input, 1 being the standard output and 2 being the standard error. So whenever you're performing file input output operations, there are 4 key system calls that are performing those input output operations. So the first one is open. This is used to open the file which is identified by the path name which is passed in its argument. Then we have the read, which reads a number of bytes and the number of bytes is denoted by count within its argument. And then we have the write. Now the write system call is used to write a number of bytes which is again denoted within its arguments from the buffer to the file descriptor or to the file referred by the file descriptor. And lastly we have close. The close system call closes the file referred by the file descriptor so that the file descriptor can free up the kernel's resources. Now there is an interesting fact that if we write a program using only these system calls, then that program will work on any type of file. So now let's talk about the open system call. Well, the open system call can either open an existing file or create and open a new file. The syntax of the open system call is as, now you can see that we need to include the following libraries. The first is the system/stat.h or sys/stat.h, and the other file that we need to include is fcntl.h. Now this function takes in 2 arguments. The first is the path name and the second is an integer flag. Now this flag can contain modes as well. Upon success, this function returns a file descriptor. Upon failure, the open system call does not only return -1 but it also sets the error no to a specific value. The flag's argument is a bit mask that specifies the access modes for the file. Now these access modes are being displayed. So you have the read-only mode which is denoted by O_RD only, and then the write-only mode, well you know what it does, and then you have the read and write mode which is denoted by O_RDWR. So whenever you are working in Linux operating system and you are trying to learn some new functions or new system calls, what you need to do is you need to open up a terminal, and then in that terminal you need to open up its manual. So the manual for open file is located on its second page. So you type in the following command which is the man to open, and then you will have the manual of the open system call. Let me increase the size of it. So as you can see, to use this system call, you need to include these 3 libraries. I'm just going to copy them just to save time. And then you have the following system call. You can read the description for this system call over here, and then you can even learn about all the different modes or all the different flags that are acceptable by this system call. So we have the append. The file will be opened in append mode, which means that when we are using the write system call along with the open system call, we would be able to write data at the end of the file. And then we have all the other system calls as well. So let's create a new file. Let's call it open basics. So in this file, I'm going to paste the libraries that are needed for the open system call. So we need a file descriptor, and we know that file descriptor is of the integer data type. And then we're going to give it some value using the open system call. And let's say what are the files that we have. So we have this file demo.c. Let's try opening this file. Inside double quotation marks, I'm going to write demo.c and I'm going to simply say like, then simply print me something like error while opening file. So you may notice that I have not given it any access mode. So let's give it an access mode of read only. Also I've added this one line just to tell us that we were able to open the file. Otherwise we would have no way of telling that if we were able to open the file or not, because we're not using any other operation to read data from the file or write data to the file. So then open up the terminal and compile the file and then run the file. And as you can see, we get the message that FD was able to open the file. Now we know this because we were able to get some value inside the file descriptor variable. Now this open function can also be used to create a file if there is no file. So for that, let's try opening a file which does not exist. Let's try to open a file like XYZ. Now we know that there is no such file in this folder. Let's change this error message, no file, or I should say no such file. Now if I open up my terminal, recompile it and rerun it, I'll get the error message, no such file. So let's learn how to create the file which does not exist. So in the mode, what I'm going to do is that I'm going to pass in a mode which is the ocreate. Now this is not a typo, this is not a mistake, this is not create, it's actually create. Now you know that whenever a file is created or a file has different permissions, so in here I want to define those permissions as well. So I'm going to define read-write permissions for the users using the following flag, and I want to give no rights to all the other users, so I'll use the following flag. You can read about these flags if you open up the terminal and open up the manual page again. If you scroll down, you will be able to see all the flags just like over here to give permissions to users, groups and others using the following flags. So now I'm going to save this file or save my program, close it, use my terminal to compile it, and then again I'm going to open or run the program. Now as you can see, as soon as I hit enter, I was able to create this file. So that is how you use the open system call to open up an existing file or to create a new file and then open it. The newly created file is also referred to the file descriptor. To demonstrate this, I'm going to use an else statement. The newly created file was also opened. So for that I'm going to delete this file. You can also use a command to delete this file, but I'm just going to show it to you anyways. Recompile my code, rerun it, and there we go. We see that there was no such file as XYZ. This file was created and it was also referred by the file descriptor. Let's talk about the write system call. Well, the write system call is pretty straightforward. We are going to use this call to write data to a file. So let's simply go over the syntax of the write system call. If you look at your screens, we need to include this library which is the unistd.h. Now this contains the write system call. In the write system call returns a size data type. It takes in a file descriptor and it takes in a buffer or a pointer to the buffer, and lastly it takes in a count variable. Now this pointer buffer is going to be the strings or data that we are going to write to the file, and the variable count defines the number of bytes or the number of characters to be written to the file. Remember that the size of the buffer cannot be less than the size of the count. However, the value of the buffer or the size of the buffer can be greater than the size of the count variable. Well, this whole write function returns the number of bytes written upon successful execution, and upon an error it returns -1. So let's quickly create a new program and we are going to call it write demo, or let's simply say it write. In this program, the first thing that you want to do is include all the libraries. So I'm simply going to write all the libraries that I'm going to use. Okay, so we need a variable which is going to be of the integer data type, and this is going to be the size. And then we need a character array which is going to be our buffer. And then the text I want to write to the file, I'm going to write that text inside the buffer using the string copy function. And this is the important step. So to write data to a file or to read data from a file, we need to open it. So we know how to open files. We simply do this thing because we have already gone through the video of opening a file, and then we pass on the mode. And the next thing is that you want to specify the mode that is going to write to the file. What I mean by this, we have two types of modes. We have the append mode and we have the truncate mode. The append mode adds data to the end of the file. On the other hand, The truncate discards the previous data and starts writing from the beginning of the file. So for the first example, I'm going to use the append and I'm going to check for an error. I'm going to say that if my file descriptor is less than 0, which means I have gotten an error while opening the file, so I want to display something which is going to be something like there was an error while opening a file. And then we would manually exit our program. Next up, we are going to use the write system call. So the first thing that the write system call takes is a file descriptor, then it takes a buffer, and then the length of the buffer. Now you may ask that the third argument was supposed to take a count variable. Well, the count variable defines the number of bytes or number of characters that you want to write to the file. And since I want to write all the data inside my buffer, that is why I'm using the function string length. And lastly, I can just simply print something on the terminal saying like the number of bytes written to the file are as, let's check for any errors. Okay, I need to change this to fcntl. So save the program, open up a new terminal, compile the program, and then simply execute the program. And as you can see that it says the number of bytes written to the file are as 36. So let's check the file. We had the file xyz that we created in the previous demo, and there you go, I am written to the file year. Now what happens if I execute the program? So let's reload the text file, and you can see on your screen that now I have multiple lines written to the file. Now this is all because of the opening mode that we used, which was the append. Now in case if I open up my code once again and I change my append to truncate mode and save the program, recompile it and re-execute it, you would see something weird. My previous data was removed from the file and the new line was printed at the beginning of the file. Also remember, if you want to learn more details about these system calls, you can always open up the manual about these system calls and read the description and all the details from here. But that was it for the write system call. So we have successfully written data to a file, but let's try reading that data. To read data from a file, we have the system call read. If you look at your screens, you have the syntax of the system call, which is exactly similar to the write system call. So again, we have to include the library unistd.h, and then we have the first argument, which is the file descriptor, which is going to be referring to the file from which we are going to read the data. And then we have the buffer. This buffer would contain the data read from the file. And then we have the count variable. This would determine how many bytes of data that we want to read from the file. Just like in the write system call, the size of the buffer should be greater than the size of the count variable. So now let's create a new terminal, or open up a new terminal and create a new file. I'm going to call it read.c. And in this file, the first thing that I'm going to do is add all the libraries that we have used. So the first thing that we're going to do is create a file descriptor and a size variable. Let's just call it sc. And then we want a character array. Then again, it's going to be buffer. And let's say we have 100 bytes again. This time around, I'm going to put some values inside it. And the first thing that we need to do is to open up the file using the open system call. So we know that our file is xyz and we want to open it in read-only mode. Then check for the error. And then we're going to call the read system call. We're going to pass in the file descriptor, and then we are going to pass in the buffer and then the number of bytes that we want to read. So let's put 10. Next up, we want to display the output to the terminal using a print function. So let's save the file. Let's open up a terminal. Let's compile this code and let's execute this code. So we got nothing from the file. Why is that so? Well, let's check the file and it was empty. So let's write something over here. This is data from the file. So let's try rerunning the code, and this time around we were able to read 10 characters or 10 bytes of data. However, this is not all the data inside that file. So how would we determine the number of bytes to read from the file to reach the end of the file? And how we can stop this from happening, which was reading an empty file and not getting any output? Well, if a file is empty, it contains something which is called as the end of the file. Well, all the additional information containing such scenarios are going to be made in a separate video at the end of this section. So we know that a file is considered to be a continuous set of bytes. Now whenever we're trying to perform some operation on the file, for example when we want to read something from the file or write something to the file, we have something called an offset. Well, there is an internal indicator present which points to the offset bytes of the file. This offset is used to read and write the next set of bytes or data from the file. Whenever we have performed an operation, the offset is updated, or we can say that the indicator is updated. Well, the lseek is a system call that is used to change the location of that particular offset or the read-write pointer of a file descriptor. Now the location can be set to absolute terms or even relative to the previous location. To use the lseek system call, we need to include the library unistd.h, and the syntax of the lseek system call is as following. So as you can see that the lseek function takes in three parameters. The first is the file descriptor, second is the number of bytes of the offset, and the third parameter is whence. Now this whence is actually an integer value, but these are predefined integer values such as seek current, seek set, and seek end. Now the seek set argument is used to change the pointer to point at the value starting from the start of the file plus the offset byte that we have given to the second argument. Similarly, the second argument, which is the seek end, is used to change the pointer towards the end of the file, while the seek current argument is used to maintain the current position of the pointer and then add in the number of offset bytes that we have put in the second argument. So as you can see that we have this program right over here. So what we are doing in this program is that first of all we are creating these variables. Now the sc variable would be used when we are performing some input-output operation on the file, while this variable, which is the seek position, is going to be used to get the return value from the lseek function. So first of all we are opening the file name xyz.txt with the read-write permissions, and then we are checking for errors. If there is an error, then we are prompting the user that there was an error opening the file, and then we are manually exiting the program. And then we set the pointer from the start to offset of 5 bytes. So if I open up my file, which is xyz.txt, you can see that there is this sentence in this file that says this is the data from the file. So we are moving the pointer to 5 bytes. This means that we're skipping the whole word this and then the space as well. And then a pointer points at I. After changing the pointer's location, we are reading the data from the file and storing it inside the buffer array. After we have read that data from the file, we are printing the data on the terminal. And then we are again using the lseek function to change the pointer's location towards the very end of the file, and then at the end of the file, we are using the write system call to print this line to the file. So if we save this program, open up a new terminal, compile and run this program, you can see that first of all we are reading the data from the file, which is data from. Now you already know that when we use the read system call, by default it reads only 10 bytes of data. So that is why we are only getting is data fr. And if we open up the xyz.txt file once again, you can see that we have added another line, or we can say that we have appended this line, that I have added this line using the lseek function with the seek end. Anyways, that was lseek system call for file operations. So now let's talk about something that occurs when two or more processes are trying to access a shared memory resource or any resource. So we have this thing that is called a race condition. A race condition is a situation where the result produced by two processes or even threads operating on a shared resource results in an unexpected way on the relative order in which the process gains access to the CPUs. For example, if we are running two programs and both of them actually try to make the same file. So in a case where the file does not exist, and when we try to run both of those programs simultaneously, both of those processes would result in saying that we have created the program, but we won't actually know which was the process that actually created that particular file. So to explain it with a code example, you can see that we have two files over here. One is called the race1.c and the other is race2.c. And inside that file, you can see that we are trying to open up the file, which is the log.txt, with the read-write access. And we are saying that if there is no such file as log.txt, then first of all sleep for 5 seconds and then create that particular file, which is log.txt, with the following permissions. And once you have created that file, you need to prompt the user that program 1 has created the file. And if I open up the race2.c, the only difference is that when the file is created, it prints out that program 2 has created that particular file. So let's first try this thing, that let's open up a new terminal and let's compile both of these programs. And then let's execute both of these programs one by one. As you can see, after a delay of 5 seconds, program 1 creates the file, which is log.txt. Now if I delete this file again, and this time around if I run the second program, which is race2, it prints us that program 2 has created that file. Now the thing is that if the log.txt is already present in the folder, and if we try running any one of these programs, for example let's say race2, we won't get that output on our terminal which says that this particular program has created that file. So to run these programs simultaneously, we would have to create a shell script. Now to create a shell script, simply type nano and then the name that you want to give to that particular script, followed up by sh. Now in this file, type the run condition or the run command for the programs, which is /race1, put an and symbol, and then the second command, which is race2. Now save the program and exit the file. Now what you need to do is that you need to make sure that this particular shell script has the executable permissions. So for that, let's check for the permissions. Now you can clearly see that the shell script does not have the executable permissions. To change that, type in the command chmod, then followed up by the permissions. I'm just going to give it 777 and then the name of the file, which is run.sh. Now I'm going to execute that shell script run.sh, which is in result going to execute both of my program race1 and race2 simultaneously. So now when I execute this program, what should happen is that one of the programs should create the file which is log.txt, and the terminal should show us which program actually created that particular file. So as you can see, after the delay of 5 seconds, we get a message on the terminal that program 2 has created the log.txt file. Also, that program 1 has created the log.txt file. Now, this is what we mean by race condition, because the output is totally unpredictable and we do not know for certain which program was the one that actually created that log.txt file. Now to further demonstrate this race condition, we have two more programs. We have named them race around 1 and race around 2. Now what these programs do is that we open up the file, which is the log.txt, which we have just created, and then we print out a character which is a 99 times, and then we close that file. Similarly, in the second program, rather than printing the character a, we are printing out the character b. So if we compile both of those programs, and then if we try to execute our shell script, which actually runs the program race1 and race2, you can see that on the terminal we get the prompt that program 2 has exited and program 1 has exited as well. But when we check the log.txt file, we can clearly see that there is no order in the output. And to even demonstrate it once more, if we Ctrl+C to stop the execution and rerun the shell script, you would have a totally different output this time around. So that is the race condition, in which multiple processes are actually trying to race against each other to access a shared memory resource. Now this is caused by the resource scheduler actually failing to give a process a particular time to execute and then moving the control to the other process. So in the previous video, you have seen what race condition is. Well, we have a concept in Linux or in system programming that is called the atomicity. Atomicity is a condition in which the code is written in such a way that code cannot be run by other processes or threads at the same time, which means that if a process is executing a shared memory resource, the other process cannot access that shared memory resource unless the first process completes its execution and tells the kernel that it has completed its execution, and then the kernel would give access to the process number 2 to access that shared memory resource. Now, as you already know that all system calls in Linux are executed atomically. By this we mean that the kernel guarantees that all of the steps in a system call are completed as a single operation, which means that there are no intermediate results. Now this concept of atomicity is very much important to maintain in a multiprocessing environment like we have Linux system, else the race around condition can occur multiple times. So if you look at this figure right over here, you can see that we have two processes, and then both of these processes are trying to access this code or this part of the code which is known as the critical section. Now if we do not have the atomicity, what would happen is that both of these processes would race each other to get that particular critical section, and every time the results would be unpredictable. And by putting in the condition of restricted access to processes by the kernel, we can achieve atomicity. So what is a process? A running execution of a program is known as a process. So simply say that whatever we code over here in our C file or C programming language, this is known as the source code. So what happens is that now this source code is converted into object file by the preprocessor and the compiler. And after compiling the object file, the linker links these header files with this program. After this program has been successfully compiled into the object file along with the libraries, it is converted into an executable format. Now if we look over to our folder, we have some .c files which are our source codes, and then we have the executable file which we compiled using the GCC compiler. Now this is the executable file which when executed would be considered as a process. So we can say that a program is considered to be a process while it is executing within the memory. So if you look over here, we have a very basic program. It is not yet compiled and it is not executing. So if I open up my terminal and compile it using the GCC compiler, so this is our source code and this would be our process code or the process executable file. And then we can execute this process using the following command. And now it is executing for 5 seconds, and within this time it is known as a process. And after those 5 seconds which we have put in the sleep condition, this process terminates and it does not exist any longer. So that was the introduction of a process. We have talked about the process IDs and the parent process IDs in the beginning of this course, but now we are going to talk about them in a little more detail. What we are going to do is that we are going to demonstrate the parent process ID and the process ID. By now, you must have an idea that Linux processes have a parent-child relation. A process is only created by its parent. No process can exist without its parent. Now, whenever the Linux system starts up, process 0 is the first process to start up or to execute, and it is called the swapper process. And then we have the process whose value is 1 or whose ID is 1, which is known as the init process. Now, init process plays an important role as it creates and monitors set of other processes. And in case you are running a process or you have executed a process whose parent has died or whose parent has finished executing, then init would become the parent of that orphan process. And yes, there is a term called orphan processes whose parents have finished their execution. Now there can only be a limited number of processes that can execute on your machine. And if you want to get the number of the total amount of processes that can execute on your machine, then type in the command cat then /proc /system or sys /kernel /pid_max. So as you can see, the total number of processes that can be run on my system are this. And now if you want to get the list of all the processes running on your Linux operating system, then there is a command which is ps -ef. Now this would list all the processes running on your Linux operating system along with the user which has executed that process. Now let's talk about getting the process ID of a process. Well, there is a function getPID that returns us the ID of the process that executes that command. And to be able to execute that particular command, you need to include the library which is the unistd.h. Open up a terminal and create a new C file. So in here, I'm simply going to use a printf statement and say something like process ID is equals to, and then use the function getPID. And as I've talked about that every process has a parent process as well, so therefore I'm going to use another printf statement to say something like parent process ID is equals to the following, and the function for that is getPPID because that stands for get parent process ID. And then I'm going to put a simple sleep condition so that my process stays in the memory for, let's say, 7 seconds. And then I'm simply going to compile and execute that program. Now as you can see, while that program was executing, the process ID was 3933 and the parent process ID was 3915. Now the cool thing is that the parent process ID is actually the ID of this particular terminal or this shell that has executed the command to run that process. So if I rerun this code, I would get a different process ID because the process is now getting a different ID from the kernel, but I would still get the same parent process ID because the same shell is running the process. Now if I do this thing, if I type in the command ps -ef and then put a pipe symbol and use grep, and then I would type in the name of my process which is simply process, and if I run this process once more and run this command over here, you can even get the process ID and the parent process ID from this command which is the Linux own command. Anyways, that was how to get parent process IDs and process IDs in the Linux operating system. So let's talk about process states. So we know that a process is created using a fork system call, and whenever a process is created, it is said to be in a create state or a created state. And while the process is running in the main memory, it is said to be in the running state. Now, even within the main memory, it is subdivided into 3 different states. The states are ready to run or waiting state, sleep state, and the blocked state. Now all of these states can exist in the main memory, or if the swapper swaps them out of the main memory, then they exist in the swap memory. And when the process finishes its execution, it is said to be in the terminated state. So if you look at this diagram over here, you can see that the fork system call is creating a process, hence we have this created bubble. And once the process has been created, it is said to be placed inside the waiting state. In this waiting state, the process is said to be ready to run, which means that it has acquired all the resources required for the process to execute. And when the preemptive scheduler schedules some CPU time for this process moves from waiting state to running state in the kernel memory or the kernel mode. Now oftentimes, from this running state, the process goes into either a blocked memory state or sleep state. Now if a resource of a process is blocked by some other process or is being used by some other process, then the process is removed from the running state to blocked memory state. And if the process executes a sleep command or the process is waiting for something, then it is said to be in the sleep state. Now all of these states, which is the waiting state, sleep state and the block state, exist in the main memory. But as we know that main memory is precious and we need it for some other processes as well, that is why the swapper swaps out the process from the main memory to the swap memory. And once the process finishes its execution, the process is taken to the terminated state. So now we know what a process is, and we even know what is a process ID and what is the parent process ID. We are familiar with the 0 process and the 1 process as well. So now we should dive deep in the memory layout of a process. So there are different segments of a process in the memory. These segments are namely text segment, data segment, stack segment, and heap segment. Well, the text segment is used to store the code, or we can say that the code resides here. The data segment is used for data variables during the compile time. There are two types of data segment, or we can say that the data segment is further divided into two parts, one being the initialized data segment, which is used to store initialized variables, and the other one being the uninitialized data segment, which is also known as the BSS. This is used to store uninitialized variables. Then stack is used for local variables. Heap segment is however a little different. It is used for dynamic memories data. So if we talk about the text segment of a process, the text segment contains all the code of the program that is executed. This segment of memory cannot be written so that the code is not altered by any pointers. This means that the text segment is a read-only segment. So let's talk about initialized data segment of a process. The initialized data segment contains global and static variables. Remember, these are not like any global or static variables. Rather, these are those variables that are explicitly initialized with a value in the code. The uninitialized data segment contains global and static variables that are not explicitly initialized in the code. However, the system initializes all values of this segment to 0. Now let's talk about the stack segment of a process. The stack is a dynamically growing and shrinking segment containing local data or functions. One stack frame is allocated for each function that is called. A frame stores functions' local variables as well as the function arguments. Lastly, we have the heap. The heap is an area from which memory can be dynamically allocated at runtime. But remember that this allocation of memory is only for variables, or I should say mostly for variables. So now let's take a look at this screen. So on your left, you can see that we have a very simple and very blank C program. There is a main function inside it, and the main function is of integer data type and it is returning 0. I'm not going to create anything, any value, any function or any variables. Now to view the memory layout of this particular program, I'm going to quickly compile it in my terminal, and then I'm going to get the size of it by using the size command and then followed up by the object file which was process. So there you go. This is the total number of bytes that this whole text is taking, and the data segment is of 554 bytes, and the uninitialized data segment, which is the BSS, is of 8 bytes because we have not made any uninitialized variables. Anyways, that's how you check the size of a process, or I should say the memory segments of a process. So in this video, we are going to talk about the dynamic memory allocation in the Linux operating system. So we have two main functions that help us to dynamically allocate some memory when required, and those functions are malloc and calloc. So if I want to read the manual for those functions, then I would open up my terminal and type in manual and then calloc. I can even type in malloc, but it's the same thing. So as you can see, this manual page is also showing us some other functions which are realloc and realloc array, but these functions are not used as much as malloc and callocs are used. So what do these functions do? Well, malloc is used to assign a particular amount of memory to a pointer variable. Well, while calloc is used for the same purpose, but the only difference is that malloc fills up that memory with the garbage values while calloc initializes that memory with zeros. So if we look at our code over here, in this program, we want to create an array of 10 integer values. So for that, we need to know the size of the integer data type. So we start off by creating a pointer to the integer data type, and we are setting that pointer to null. And then we want that pointer variable to point to some memory location. So for that, we are using malloc at first. Now we know that we want to store 10 values of the integer data type. Therefore, I am using 10 multiplied by the size of the integer data type. Then in this if statement, I am simply checking for some errors. Basically, if malloc does not work, my pointer would still remain null. So I'm simply checking whether my pointer is null or not. If it is null, I'll simply exit from the program, and if it is not null, then I'll carry on with the program. And just to demonstrate this code, I am just running a for loop to fill up the 10 memory locations with some integer values, and then I'm printing those values back to the screen. And the main thing when it comes to malloc and calloc or any dynamic allocation is that at the end of the code, you want to free up that memory location. Otherwise, the process would exit from the memory, but the memory location would still be consumed by that pointer variable. So as you can see at the end, we are using the system call free, and we are passing in the name of the pointer variable. Now if I open up my terminal to compile and run this code, you would see that we were able to print out 10 values to the terminal. So now if I want to allocate some memory using the calloc function, there is one major difference when using this function, and that is the calloc function takes in 2 arguments. The malloc takes in 1 argument, which is the total number of memory that it wants. But calloc function works a little different. You need to pass in the number of memory locations that you want and then the size of each memory location. So here I changed 10 multiplied by size of to 10 comma size of integer data type. And then I can simply recompile this program and rerun it, and it would work just fine. So that was dynamic memory allocation in the Linux operating system. So in this video, we are going to talk about the command line arguments. So what are command line arguments? Well, these are those instructions that are passed to a process after the execution command of the process. For example, if I were to open up my terminal and assume that we have a process named as demo1, so the command to execute that process is /demo. Now everything I put on after this command in this particular line would become the command line arguments of this program. For example, I can say something like hello world. What I have done is that I have written a string over here, but how the program perceives it is that it perceives that it received 2 strings. Basically, every space character is defined as the difference between one string and the other string. So this program demo1 is receiving 2 command line arguments from the user. So I have this code over here which would explain command line arguments to you in a much more clear way. So in the main function, we are actually defining 2 parameters. First is the integer argc, and the second is the character pointer to an array, which is the argv. Now this argc is actually the argument counter. So when we pass on the arguments within the terminal, the number of those arguments is stored inside this argc variable. And then the actual arguments are stored inside this array, which is the argv. Remember that if you do not pass any arguments and simply type in the command to execute that process, there is still one argument inside the argv, which is the name of that process. So if you want to write a code to print out the command line arguments given to a program, we are first declaring a variable, and then we are saying that if there were no arguments passed to the process, which means that only the process name is inside the argv array, then prompt the user to provide some kind of command line arguments. Otherwise, it would print the total number of arguments and print those arguments onto the screen as well. So simply open up a new terminal, compile this code using the GCC, and then execute the program by typing in the name, which is clargs, and then I'm going to pass on some command line arguments. Let's say welcome to Linux system programming. So there you go. As you can see that we have total number of 6 arguments. The first is the name of the process, which was clargs, and then every individual word was taken as a separate command line argument. So the first became welcome, then to, then Linux, then system, then programming. So these were the command line arguments that you can use in the C programming language for system programming in Linux. So in this video, we are going to talk about creating new process using the fork system call. So process creation is really necessary because with the help of process creation or new processes, we can divide a big problem into smaller chunks and have multiple processes work on different chunks at the same time. Now we have mentioned that the fork system call is used to create multiple processes, or I should say new processes, but the thing is that the fork system call seems very daunting when you first start out with the fork system call. So worry not, we are going to break it down to you, and we are even going to show you the memory diagram to represent to you how fork system call actually works. Let's talk about fork system call. We already know that the fork system call is used to create a new process. Well, the thing is that the process that is created is known as the child process. Now what do we mean by this? Basically, the program that you are running or the code that you're running in which the fork system call is included is known as the parent program. And the process that is created as a result of that particular code is known as the child program or the child process. By the way, when the fork system call is made, the resulting child process is an exact duplicate of its parent process. We are going to explain what we mean by this exact duplicate statement. Anyways, let's talk about the syntax of the fork system call. So, to use the fork system call in your C program, you need to include the library which is the unistd.h. So, the return type of the fork system call is a PID_T. And then this fork system call does not take in any parameter, it's a void argument function. However, the fork system call creates a new process, so the fork system call returns values to both the parent process and the child process. Now, how is that so? Basically, in the parent process, it returns the process ID of the child, and in the created child process, it sets that ID to 0. Remember, the child's process ID is not 0. Rather, the return value from the fork system call in the child process is 0. Again, when we move on to the code, you would better understand all of these things. So, before moving to the code, we need to understand one simple thing. Just take a look at this particular diagram. You can see that before executing the fork system call, there was only our parent process in the virtual memory. But as soon as we invoked the fork system call, there were two processes residing in the virtual memory. Now, as you can see, the parent process and the child process are linked to each other, as we are calling them parent and child. However, their virtual memories are totally separate from each other. So we have this code to demonstrate the fork system call. Now, I'm going to go with this code very slow and explain everything because again, fork system call seems to be very daunting at first. It is kind of a complex thing to grasp. We have included the standard libraries, and we have included the library which includes the fork system call, which is this unistd.h. Now let's head inside the main function. So the very first thing that we're doing is that we're creating a variable of the data type PID_T to store the return value from the fork system call. So we know that we are going to create a child process in this program. So that is why we are creating this variable. Now the very first thing that I am doing is that I am printing to the terminal the process ID of this parent process even before executing the fork system call. After that, I am executing the fork system call and storing its return value in the variable that we created, which was ID. Now, here comes the cool part. From the point the fork system call is invoked, the rest of the program is exactly duplicated in the virtual memory of the child process. So basically what this means is that everything onwards from here exists in two places in the virtual memory. Once inside the parent process and once inside the child process. So now what we are going to do is that we are going to go over this particular set of code twice. Once with the respect of the parent process and the other time with the respect of the child process. So assume that we are the parent process. Now previously I've shown you that upon success of this fork system call, the parent process gets the ID of the child process. By the way, over here we're just checking if there was an error invoking the fork system call. If there was no error, this whole statement would be ignored. So we'll start from here. So if the child process has some kind of process ID, then the returned value in this variable ID would be greater than 0. If that is the case, then we would know that we are inside the parent process. So we can print something like the parent process has created the child process with the ID, and then we can simply pass on this ID number returned from the fork system call. So if we see this output on the terminal, then we would know that this came from the parent process. Now, if the ID number is less than 0, then that means that there was an error. And if the ID number was greater than 0, then that means that child process was created and the ID was stored inside this ID variable. But if the ID is 0, then that means that we are inside the child process's virtual memory, because the fork system call would return 0 to the virtual memory of the child process. So the very first thing that I'm doing over here is that I'm printing out that I am the child process and my ID is, and I'm using the ID variable we created over here. Second time, as I've mentioned, I want to check the function getPID. So therefore I'm saying that the child process's ID by using the getPID function is as, and then I'm passing on the getPID function. And as I've already talked to you in the beginning of this course that every process has a parent process ID. So therefore while we are inside the child process, we are going to check for the parent process ID by using the function getPPID. So now if I save this program, compile it and execute it, you will get the following result on the terminal. The parent before executing the fork system call prints out its ID, which is 4275, and then it creates a child process with the ID 4276. As I've already mentioned that the fork system call returns the ID 0 within the child process. So when we checked for the child process's ID using the ID variable that we created, we got 0. This means that we are inside the child process. And while staying within the child process, we are using the getPID function to get its actual process ID, which is 4276, and which matches the result we got from the parent process, which is 4276. And then again from within the child process, we are fetching the ID of its parent, which is 4275, using the function getPPID, and again it matches the process ID which we got from the parent process. So that is how you create a child and a parent process using the fork system call. I know this example was very weird because I wanted to show you the return value from the fork system call and how you can differentiate the child process and the parent process from staying within the same code by using the ID returned from the fork system call. Now you know that these if and else statements were a way to differentiate between the child and the parent process. But what if we did not have these conditions? So we have a very simple program over here. We're simply creating an ID variable and calling the fork system call on that ID variable, and then simply printing out the statement, hello world, it's Linux. So what should happen? Basically, as soon as this fork system call is invoked, all the other lines below it are duplicated. So we should see two of these lines printed to our terminal, one from the parent process and the other from the child process. So let me just compile this code, and as you can see on your screen that we got two outputs. One was from the parent process and the other one was from the child process. So that is how process creation is done using the fork system call. So in this video, we are going to talk about the exec system call, or which is the execute system call. So we know how to create a child process, and we know that the child process has its own virtual memory. But sometimes we do not want to write the code of the child process all in one single program along with the code for the parent process. So in that case, you can also divide multiple processes in multiple .c files, and then you can create a child program and then use the execute system call to run that particular program in the virtual memory of the child process. So how do we do this? So you can see on my screen I have two programs opened. One is the exec1 and the other is the exec2. So let's talk about the exec1 program. So first of all, I am creating a child process ID of the data type PID_T, and then I am calling the fork system call to create the child process. And then I'm simply checking for errors in the creation of the child process. If there are no errors and if we are inside the child process, I'm simply printing out that currently I'm inside the virtual memory of the child process before the execute system call. And then what I'm going to do is that I'm going to call the exec system call. I'm going to use the exec function to execute my program, which is the exec2. And I can also, after the comma, pass in arguments and then another argument, and when I want to end the arguments, I would simply type null after a comma. Now this would place the exec2 program into the virtual memory of the child program. Now this line should be present in the child virtual memory, but after it has been replaced by the exec2 program, this would not be able to run. And by the way, in the exec2 program, I am simply printing out that hello, I am the second program. And in the parent program, I'm simply printing out I am the parent program. Let me just change it to process, just to better understand this whole code. So now I have my terminal over here, and what I am going to do is that I'm going to compile both of these codes. Remember, you need to give the same name as exec2, which is in the code inside the exec function. Now I can simply call the first program, which was the exec1, and just like that you can see that this is the output from the parent process, and after this the parent process ended its execution, and inside the child process we got this output before the second program was placed inside the memory of the child process. And after the execution of the exec system call, the second program took the place inside the virtual memory of the child process and printed out its instructions. And as you can see, we were not able to print out this line
because this was not the part of the second program, rather it was the part of the child program. So we can say that the exec function not only places the second program in the virtual memory of the child process, rather it overwrites the child process. So that was exec function in the Linux operating system. So in this video, we're going to talk about process monitoring using the wait and exit system calls. So as you can see, I have this code on my screen. So I'm going to go through it and I'm going to explain how we can use the wait and exit system call to monitor the execution of the child process and even stop orphan processes and zombie processes from ever existing. So starting off, I have created this variable cpid to store the return value from the fork system call, and then I've created an integer variable status to get the value of the status of the child process. After that, I have invoked the fork system call to create my child process, and I'm storing that ID of the child process in this variable, which is cpid. And then I'm simply checking if there is an error creating the process in this if statement. And if there is no error and we are inside the child process, which means that the cpid is equal to 0, then what I am going to do is that I am going to print out the ID of the child process using the function getPID, and then I'm going to put the child process to sleep for 15 seconds. Let me just increase it to, let's say, 25 seconds. After those 25 seconds, what I'm going to do is that I'm going to have my child process print again to the terminal saying that my child process once more is this, and I'm going to exit now. And then I'm going to use the exit system call to exit the execution of the child process. Now, why is this exit system call really important? So basically what happens is that if I do not exit this program, my child process could become a zombie process. Basically, what a zombie process is that it has finished its execution but it did not terminate itself. And after some time, this zombie process could become an orphan process. So what is an orphan process? Basically, an orphan process is a process whose parent has died, or I should say whose parent has finished its execution. So you need to make sure to add in this function, which is the exit in the child process. And to stop from orphan process from ever existing, you need to include the wait system call in the parent process. So let's go over that right now. So in the parent process, I'm simply explaining that, okay, we are running the parent process before executing the wait system call. And then I'm saying that wait for the children of this parent process to finish their execution. Until then, halt the execution of the parent process. And this wait system call is going to wait for a signal from any of the child. After I've received a signal from one of the child that it has finished its execution, what I'm going to do is that I'm going to print out the following line that the parent is done waiting and the parent process ID is this, and the child process ID which has been returned is this, whose processing has finished. And then I'm going to print out the status of that child process. But for now, I'm going to remove this line for the status because it has some purpose and I'm going to show it to you in a minute. So what I'm going to do is that I'm going to compile this code and run it. So as you can see, the parent is executing and the child is also executing. But right now, the child process is sleeping for 25 seconds. That is why all of these lines over here are not being executed in the parent process. That is because it is still waiting for a child process to finish its execution. And just like that, once the child process has finished its execution, the parent process says that, okay, my child has finished its execution, so I'm going to continue my execution and terminate. Now another cool thing is that if I rerun this code and if I open up another terminal and use it to kill the child process, my parent process would start to execute its execution instantly. What this is that it doesn't matter how the child process ends its execution. What matters is that the child process is no longer in the memory and the parent process can continue its execution. We can even get the status of the child process by using this line, which is the wait, and then I'm going to pass in integer variable which I've created over here, which is the status. And lastly, the line I commented out, I'm going to add it back to the code, recompile my code and re-execute it. Now if I kill this process, you would see that I get the command or the signal that killed this child process in the status. Now if I want my parent process to wait for a specific child to execute, then I have this function which is the waitPID. In here I need to pass in the ID of the child process, which was cpid, and then if I want the status, I can get the status again. And in the third argument, remember that waitPID function takes in 3 arguments. First is the child process ID, second is the status, and the third is the option. So I'm going to go with the default, which is the 0. If you want to read all of these options, you can open up the manual page for the waitPID command and read the options from there. So now if I save this program and re-execute it, and if I kill this program, everything would work fine. So basically this time around, the parent process is not waiting for any child to finish its execution. Rather, it is waiting for a specific process ID to finish its execution, and after that specific child has finished its execution, the parent process is about to continue its execution. So that is how you can monitor the execution of the child processes from the parent process to avoid orphan processes and zombie processes using the wait and exit system calls.
So now let's talk about signals. So a signal is a notification to a process that an event has occurred. Signals are sometimes described as software interrupts. We have talked about signals in the fundamental concepts section as well. So signals are analogous to hardware interrupts, in that they interrupt the normal flow of execution of a program, and in most cases it is not possible to predict exactly when a signal will arrive. And that is also why a signal is said to be asynchronous. A process can send signals to other processes, or a process can even receive a signal from the kernel. Upon delivery of a signal or upon arrival of a signal, a process carries out one of the following default actions. Now, these default actions depend entirely on the signal. So the first action is that the signal is ignored, which means that it is discarded by the kernel and has no effect on the process. The second action is that the process is terminated or killed. This is sometimes referred to as the abnormal process termination. The third action is that a core dump file is generated, and then the process is terminated. A core dump file contains an image of the virtual memory of the process, which can be loaded into the debugger in order to inspect the state of the process at the time that it was terminated. Then the next action is the stopped execution, which means that the execution of the process was suspended. And following up from the previous action, the next action is the execution of the process is resumed after previously being stopped. Now the last action that can be performed upon the arrival of a signal is that a signal handler is executed. In Linux operating system, each signal has a specific name, but the kernel does not recognize the signal from its name, it actually recognizes it from its number. So every name of a signal has a corresponding number, which determines what are the actions that are going to be performed by the kernel. So if you look at the table right now, first off we have the signal abort, and the signal number is 6. So the description for that signal is abort process. Similarly, we have a whole list such as signal bus that has the number 7, and the description is that it is a memory access error. Similarly, there are various signals listed here along with their numbers and along with their description as well. While mentioning the actions that are performed by a process upon the arrival of a signal, we mentioned something which was a signal handler. A signal handler is also known as a signal catcher, is a function that is called when a specific signal is delivered to a process. Now, invocation of a signal handler may interrupt the main program flow at any time. The kernel calls the handler on the process's behalf, and when the handler returns, execution of the program resumes from the point where the handler interrupted the process. So if you look at the diagram, we have the main program with its flow of execution, and this program receives a delivery of signal. Upon this delivery of signal, the kernel calls the signal handler on behalf of this process. Due to this, the flow of execution changes and the flow goes inside the signal handler. Now the signal handler executes the code based upon that particular signal and then returns the flow of execution back to the program. Then the program resumes the flow of execution in the normal way from exactly where it was interrupted. So that was the introduction of signals and signal handlers in the Linux operating system.
So now let's talk about the basics of programming with signals. So in the previous video, we learned about what a signal is and how a signal is processed or how a signal is executed for a process. But now we are going to be focused on how to write C programs which have some signals included in them. So the very first thing is that if you want to work with signals in the C program, you need to include the library which is the signal.h. And then we have a function which is named as the signal, and this signal function takes in two arguments. The first is the signal number. You are familiar that the kernel does not recognize the signals with their name, rather it recognizes them through their signal number. That is the signal number that we are going to pass in this first argument. The second argument is the signal handler. So basically, signal handler is a pointer to a function which is known as myHandler, which takes in a single argument which is the signal number, and it returns a void. Keep in mind that when a signal is delivered to a process using the signal function, the signal can either perform two options or two actions. The first course of action is to go with the default action of the signal, and the second option is that to ignore the signal and just carry on with the flow of execution of the program. In case you want to go with the default behavior of the signal, then you pass on the argument sig underscore dfl, which stands for default, in the second argument of the function signal default. And if you want to ignore the signal or ignore a specific signal, you want to pass in the argument which is the sig underscore ign. Now this would ignore the signal given by the signal number. In case you want to find every detail about signals or most of the details about the signal, simply open up a terminal and type in man space 2 space signal, which means the second page of the manual and only focusing on the signal. So let me just make it full screen. So here you can find the full name of the signal, which is the ANSI C signal handling. You can find the required library and the syntax of the signal function. Now what we want to focus is that in case of a successful operation of the signal, it returns the previous value of the signal handler. But in case of an error, it returns us a sig error signal. And also in the event of error, erno is set by this particular signal function. So if you scroll down, you would see that these are the most commonly used signals in C programming language, or I should say system programming in Linux. So if you have worked with Linux before, you might be familiar with this kill command. Now this kill is a system call which is used to kill a process. So if you want to use the signal for kill, you would have to use the function which is the integer kill followed up by PID, which is its first argument, which stands for the process ID, and then the signal number that you want to use while killing that particular process. So now let's take a code example to get to know signals better. So we start off with including the signal library in our code, which you can see over here, and then let's head inside the main function. Now the very first thing that we are performing in the main function is that we are printing out the process ID of the program that will be executed in result of this code. We are doing that so that we can send signal to that particular process ID. Then we are using an if statement, and then we are checking that if we receive a signal on that specific process ID, and if that signal is sigint, by the way, sigint is sent by pressing Ctrl+C, then we need to call the signal handler function. And also we are going to check for some errors while calling or while receiving that signal, and in case of any error we are going to print out that error, and we are going to print out the prompt that we cannot handle the signal, and then we are going to abnormally exit our code. And also if that signal is sig term, we are then again going to call the function which is signal handler, and similarly we are going to check for the error. Now as you may see that this program is infinite because I have simply put a while loop and I have not put any condition to terminate this while loop. So this program would stay in the memory for an infinite amount of time unless I get a signal from outside which would kill or exit this process. So let's now head inside the signal handler function. So as you can see that my void signal handler function is receiving a signal number from this line over here, and we are saying that if that signal number is sigint, then what I want to do is that I want to print that I have caught the sigint signal. And if that signal is sig term, then I want to print out that sig term has been caught by the process. And after that we are going to exit the program since it was an infinitely running code. So I want to exit it after I have handled those signals. So if I compile this program using my terminal, and if I run this code, first of all you can see that the process ID is 3342. And if I want to send in the sigint, I would simply press Ctrl+C. And as you can see, it says that it caught a sigint signal and it executed its processing. So let me try something out. So if I come to my code and comment out this whole section, which was to manage sigint, and if I simply put in the default behavior, and in the second argument of the signal function I'm going to go with the signal default flag, and I'm again going to compile this code and execute it. So now if I press the Ctrl+C command, you would see that it has terminated its execution, but it has not prompted us with anything. Now why did it terminate? Basically sigint, which we send with the command Ctrl+C, is used to exit the processing of a program. So that is why it went with the default behavior, which was to exit its processing, and it did not go inside the signal handler function. So what would happen if I override this default action but I do not exit the program upon receiving that signal? So let's recompile the code and let's rerun the code, and now I'm going to press Ctrl+C. As you can see that it caught a sigint, but the thing is that it did not kill the process. So if I press the Ctrl+C command once again, I would get another prompt, but the program would not stop executing. So it is a very good practice to not override the default behavior of signals. So now if I want to kill this program, I would have to open up a new terminal, I would have to use the command sudo kill -9 and then the process ID, which was 3440. And that's how I would stop the execution of this program. Let's also try giving it the seek term. So I'm going to keep this code as it is, meaning that it would be an infinite running code. So I'm going to rerun this code. The process ID is 3521. I'm going to open up a new terminal, and in this terminal I'm going to again use the kill command, but this time around I'm going to use the signal number, which is 15, which is for seek term, followed up by the process ID, which is 3521. So as you can see that our process says that it caught a seek term, but again, since we already override the default execution, the program did not terminate. So I'm going to kill it now using the signal number 9. So there you go, that's how you can catch signals given to a particular process, and you can even override their default behavior. Also, if I come back to my code over here and if I comment out this part and I change this signal default to signal IGN, which is to ignore the signal, and then I have to recompile my code and re-execute it. So now I want to give it some signal which is sigint. Now in this case the signal should be ignored. So if I press Ctrl+C, you can see that I am pressing Ctrl+C, but I'm not getting any output on my screen, neither the process is being terminated. That is because we are catching the signal and we are choosing to ignore that particular signal, which is sigint. So now if I want to kill that process, I need to pass in the seek term. Again, we know how to do this. It's sudo kill 15, which is the number of the seek term, and then the process ID, which in this case is 5541. So that is how you ignore a particular signal. Okay, so now we have another program over here. Now this program is going to handle the alarm signal, but this program is not going to get alarm from outside the process, but rather it is going to generate its own alarm and then handle it with this function. So what is happening in the main function is that we are simply saying that if it receives a signal alarm, then go to the function that is display message. And then after 2 seconds we are generating that alarm. Now this puts this code inside this function, and then we get a message that we generated a sig alarm. And after that, for every 2 seconds we generate a new alarm, and we keep printing out this message because it is now stuck in a recursive loop. So I'm going to clear out my terminals, and now I'm going to compile this program. So as you can see that for every 2 seconds I generate a new signal alarm, which prompts us a message that generated a new signal alarm. So let me just quit this program by pressing Ctrl+C. So now what I'm going to do is that I'm going to handle the very first alarm that it catches, and then I'm going to go with the default behavior of this alarm signal. So how do I do that? So in the main function, I'm going to say that for the very first alarm that it catches, I'm going to go inside the display message, and inside here I'm going to create another signal listener by using the function signal, and then I'm going to type in sig alarm, and rather than going for the display message function, we are simply going to go with the default behavior, which is the sig_dfl. So what would happen is that the first signal listener would actually put our program into this function, but then we created another signal listener on the same signal, so the previous signal listener would deprecate. So only this signal listener would be activated, and it would look for signals, or in particular it would look for sig alarm. So if I save this file, recompile my code and re-execute it, you would see that after 2 seconds I get the message generated sig alarm, and after 2 more seconds I get the default behavior, which was the alarm clock, and then the execution of my process was terminated. Similarly, I can simply change this to signal ignore by typing in IGN instead of DFL, and this time around my first alarm signal would put me in the function display message, and my second alarm would simply get ignored, and due to that every alarm after the first one would get ignored and my process would become an infinite one. So if I save this file, recompile my code and re-execute it, you would see that after 2 seconds I get the message sig alarm, and after that I'm not getting anything on my terminal. Now the alarm is being generated, but after the first one we are choosing to simply ignore it. So now if I want to close the execution of this process, I would simply use the command Ctrl+C. Anyways, that was programming with signals and how to create a signal listener and how to use a signal handler. Now that we have worked with signals, signal listeners and signal handlers, we can move on to create some user-defined signals and perform some actions upon that user-defined signal. So I have a code right over here, which is the program 1, and similarly I have another program which is program 2. So I'm going to open it side by side. So to start off, let's focus on the program 1. So what is this program doing? So what I'm going to do is that I'm going to create a child process of this program, and then I'm going to replace that child process with the program 2. So here I'm creating a PID for the child process, and then I'm calling a fork system call to create a child process. And then in that virtual memory of the child process, I'm going to start executing the program 2 using the command execute L. And then I'm going to pass in some random arguments just to showcase how to work with arguments as well. So the main thing here is that in the parent process, and yes, I'm going to call program 1 the parent process and program 2 the child process. So in the parent process, I'm creating a signal listener which is going to listen for the signal sig user 1. And upon receiving that sig user 1, it is going to print out this statement that the parent process is saying caught sig user 1 in parent. Now moving on, the parent process would not only just look for that signal, rather it would wait for the child process to complete its execution. And then I want to send a signal to the child process. So to sum it all up, what I'm doing is that I'm creating a parent-child process relationship, and I'm sending a signal from parent to child, and in the child I'm sending a signal from child to parent, and then handling them in their own respective processes. So over here I've put a sleep of 2 seconds, and after those 2 seconds I'm going to send a signal to the child process ID, and the signal is going to be sig user 2. And then I'm going to wait for the child process to finish executing, and then I'm going to print that the child process has executed, the parent process is about to exit as well. So coming to the child process, in here what is happening is that I'm simply saying that I am a new process created by the execute L system call, and then this is my process ID. And then in the child process I'm creating a signal listener for sig user 2 which would be sent from the parent process, and upon receiving that signal, the child process is simply going to print to the terminal that okay, this is child speaking and I have caught the signal user 2 in the child process. And then I'm going to print out the arguments that have been passed from the parent process to the child process. And then staying within the child process, I'm going to sleep for 5 seconds, and I'm going to print out that okay, now I'm going to send the signal to the parent process. And for that I'm again using the command kill, and for the process ID I'm using the function which is the get ppid. We have already used the get PID function, and we have also used the get ppid function. And the signal that I'm going to send to the parent process is going to be sig user 1. And then I'm going to sleep the child for 10 seconds. After those 10 seconds have elapsed, the child is going to exit, thus sending the control back to the parent process. So now what I'm going to do is that I'm going to open up a terminal and compile both of these programs. And after I've compiled both of these programs, I only need to execute my program 1, which would be my parent program. That is because, again, the execute statement right over here is going to run the program 2 in the child process of the program 1, thus consuming the virtual memory of the child process which was created as a result of the fork command with the program 2. So now to run this code, I'm going to simply type in the command ./program1. So let me increase the size of this terminal. Now as you can see, when the program 1 started, the parent process started the wait function and created the child process. And the ID of the child process was 7401. After the creation of child process, it was overtaken by the program 2 due to the execute L system call, and then the program ID remained the same, which was 7401. And then we got the arguments that were sent by the parent process to this child process. And finally, we received the signal 2 sent from the parent process to this child process. Now, in this particular case, we are only printing out that we got that particular signal, but you can choose whatever you want to do upon receiving that signal. It's totally up to you. And after receiving that signal, we're sending a signal back to the parent. And when the parent catches that signal, which is sig user 1, it prints out that okay, I've caught the sig user 1. And then after some time, the child exits its execution. The parent prompts the terminal that okay, I am done waiting. My parent ID was 7400, and now I'm also about to exit my status, which is I'm going to terminate my execution. So that is how you create a parent-child relationship and send signals from one process to another process. So now let's talk about threads in the Linux operating system. Well, a thread is a lightweight process which is also known as LWP. A process has its own memory, while a thread shares the memory with its parent processes and other threads within the process. There is something very different when it comes to Linux operating systems and other operating systems, and that is that Linux has a unique implementation of threads. To the Linux kernel, there is no concept of a thread. Linux implements all threads as standard processes, The Linux kernel does not provide any special scheduling, semantics, or even data structures to represent threads. Instead, a thread is merely a process that shares certain resources with other processes or even the parent processes, which is sometimes known as main thread. So if we look at this figure right over here, we can see that we have some segments such as heap segment, data segment, and code segment. Now we have talked about these segments in the previous videos, but the difference in the previous videos and this particular segment diagram is that we can see multiple stack segments. Now why is that so? When a process creates multiple threads, only the stack segments are duplicated, which are given the names as thread 1 segment, thread 2 segment, and so on. Now the execution of these threads is concurrent. So the scheduler is responsible for allocating some CPU time to every thread, and when the time has elapsed, the CPU is allocated to the next thread. Now let's talk about inter-process communication between the threads. Well, as you can see in the diagram, we have multiple stack segments, but we do not have multiple heap segments, data segments, or even code segments. Well, that is because the stacks, or basically the stack segment of the threads, communicate with each other through a single heap segment or a single data segment. Now, the code segment is different for every thread. However, user resources and all the other stuff required for inter-process communication between the threads placed in the heap segment and the data segment. So that was the basic knowledge of threads in the Linux operating system. Remember, there are no specific threads in the Linux operating system. However, you cannot call a thread a process just because there isn't a thread term in the Linux operating system. We would explain the creation of threads and the termination of threads in the next video. So let's talk about the creation and the termination of threads. So whenever a program is started, the resulting process consists of a single thread, which is called the initial or the main thread. So if you want to create the threads from a process, then you would have to use the function which is pthread_create function. Now to use this function, you need to include the library which is pthread.h. So let's talk about the syntax of this function. To simplify everything, this function takes in 4 arguments. The first is a pointer to thread, second is an attribute, third is a void, and the last is the arguments that you want to pass into the new thread. Remember that every time this command is executed or this function is executed, it returns 0 on success or a positive error number on error. So we can say that the return type or the return value of this function is integer. As we discussed the process IDs, you should know that every thread has a unique ID. Or we can simply say that every thread inside a process can be uniquely identified by a thread ID. Now this ID is returned to the caller of the pthread_create function, which means that if you put a variable equal to this function, in that variable you would get the ID of the thread created in result of this command. Also, a thread can obtain its own ID using the function which is the pthread_self. Now, how to stop the execution of a thread? Well, we know that thread is a part of the program. The execution of a thread terminates in one of the following ways. Either the function that was called on thread creation returns a value with the return command, thus saying that the thread has completed its purpose and terminating the thread. Or the thread can stop executing by using the function which is the pthread_exit. Now there is also a concept of cancelling, or I should say thread cancelling, and for that we use the function pthread_cancel. Now remember, our main thread is often processing within the main function. That means that when the main thread has finished executing, all the threads created within that process would terminate immediately. So let's take a look at this particular code. So you can see that I have included all the libraries that are required for this code to execute, but notice that we have included the library pthread.h. Now let's head inside the main function. So the very first thing we did was create a variable with the data type pthread, and we called this t1, and then we created an integer variable to store the output coming from the function which is the pthread_create. So within this function we passed on the thread which is t1, but not like the name of the thread, but rather the address of the thread using the address operator. And then for the attributes, we want to go with the default attribute, so that is why we use the keyword null. And then we needed to point to a void pointer. Now when I talked about this parameter in the syntax, it might have sounded very weird. Well, that is because we need to point this particular argument to a function which is the thread of this process. And then we have the arguments that we want to pass on to that thread. And then we're just simply saying that if we were not able to create that thread, then prompt the user that there was an error creating the thread. Otherwise, print out the ID of this process, or I should say the main thread. Sleep for 5 seconds so that we are able to see the processing, and then just simply say that the main thread is about to exit, and then manually exit the program using this exit command. So if we head inside that function, so first of all we are just simply getting the arguments and converting them into a string, and then we are going to print that argument that was passed from this function call onto the screen, and we are going to print out the process ID. Now remember, process ID of the main thread and the process ID of the subthreads is always similar because they all are the part of the same process, so that is why their process ID do not change. So within this thread we are sleeping for 2 seconds, and then we are saying that we are going to exit from the thread. Now I have already told you how a thread terminates, that is, the function of the thread either returns a value or some other commands which we will go in a second, but here we are returning the value. So I'm going to save it, compile this program really fast, and you can see an error because we need to put in some extra commands while compiling it. And that particular command, or I should even say flag, is gcc the source file followed up by this flag which is the lp thread, and then -o and the object file which is thread. So this should allow us to compile our program which includes some threads. Now we can execute this program like we normally do using the following command. So as you can see that main thread, or I'm going to just refer to it as the main process. So our main process had this particular process ID, and then it created a thread which was the thread func, and the arguments that were passed to this thread were hello world, and the process ID, if we checked it from within that thread, was still the same, which was 3766. And then after 2 seconds the thread ended, and after 3 more seconds, or I should say after 5 seconds of creating the thread, we exited from the main thread as well. So now you might be wondering why go through all this hassle to just simply create a function to run on its own. Well, actually the answer is within that question. Well, we want to divide our big complex problems into smaller individual threads that can work on their own, or I should say that they can execute concurrently with each other. So that is why we use threads. So now we have another program which is named as the thread1.c. Now basically this is the exact same program as the previous one with a slight change. Within the thread we are not returning any value, but rather we're calling the pthreadExit function. You can see that the thread func is going to sleep for 15 seconds while the main thread is going to sleep for 5 seconds and then exit the termination. So what would happen if the main thread exits its termination? Well, all the subthreads are going to stop their execution as well. So let's quickly compile this, and I'm actually going to open up a new terminal, or I should say a side terminal, and in here I'm going to check for processes and only show the one with the name thread1. So there is absolutely no process because I have not executed this program. And now I'm going to execute the thread1 process, and if you tally this process from the code, you can see that while the thread was sleeping, the main exited and the lines after the sleep were never executed. However, if I comment out this exit statement from the main function and simply use pthread.exit, you are going to see something really fun. So now if I quickly recompile my code, so I'm going to execute this process, and at the same time I'm going to look for all the processes with this name which is thread.win, so that I can show you guys a really cool thing. So I'm going to run this command, come over here and type this command. So our process is running. You can see a keyword defunct. So what is this? So basically what happened was that the process with the process ID 4143 had 2 threads. One was the main thread and the other one was the thread func that we created. The main thread was supposed to terminate its execution after 5 seconds, and the thread func was supposed to terminate its execution after 15 seconds. So what happened was that the thread func was executing when the main thread finished its execution, or I should say terminate its execution. So when that happened, the process became a defunct process, which means that some of the threads are still executing while the main thread has stopped its execution. So that is how even if the main thread exits its execution, the subthreads can still carry on with their own individual executions.
So in the previous video, we talked about how if the main thread stops its execution, the subthreads also exit their execution. But in some cases we do not want that to happen, and we do not even want the subthread to become a defunct thread or a defunct process. So in that case, we want to use a join, and we have a join which is the pthread_join function. And when this function is called from the main thread, it waits for the specified thread to terminate. Now, where is this thread specified? Well, it is specified in the arguments of this function. But in such a case where the thread has already terminated, the pthread_join returns immediately. So what is the syntax of this pthread_join? So the syntax is being displayed to you on your screen. Now you can see that the return value of this pthread_join function is of integer data type, and there are two parameters. First is the thread. It is that thread whose execution will be monitored, and then we have a double pointer to void, which is going to be used to store the return value from that particular thread. Now since it returns an integer value, we can simply say that it returns 0 on success, or it will return a positive error number on some kind of error. So let's add some information about this function. The task that pthread_join performs for thread is similar to that performed by the wait PID for processes. So what is wait PID? In case you don't know, wait PID is a function that waits for a specific process to complete its execution before exiting the main process. And when this same step is done for a thread, it is done by the function pthread_join. Now what is the main use of this particular function? Well, the main use case of using pthread_join is that the main thread should wait for all the threads it has created, and only then it should terminate itself, which means that the main thread should always terminate at the very end. So now we have this program to demonstrate the working of pthread_join. Make sure to include the library which is the pthread.h. So just like in the previous thread examples, we have created a thread whose name is threadfunc, or basically thread function, and that is performing some task. I would explain what this task is, but for now let's head inside the main function. We are creating a thread ID for this thread function, and this time around we are not only just creating this void pointer but actually using it to get the return value from the pthread_join function. So what we did was we simply created a thread, stored it inside a variable, saw if there was an error or not, and then moved on to the next step. What was the next step? And in the next step, we used the pthread_join for this thread ID which we have created previously, and we stored the return value in this particular variable. And then we checked for some error using the if condition. So if there was an error trying to monitor this particular thread, then it would prompt us that there was an error. Otherwise, if there is no error, this program would say that now it is in the main thread, and the subthread which was the threadfunc has returned this particular value. And after getting that value from the subthread, the main thread is going to terminate itself. So what is happening inside the threadfunc? So like we did in the previous example, the very first thing that you want to do inside a thread is that you want to get the arguments stored in a character array. After that, we are simply creating a counter variable, and we are prompting the user that this thread has started its execution. And we are simply incrementing the counter variable every 5 seconds until it reaches the max count, which is 100, which I have defined over here. And after it has completed its execution, it is going to prompt the user that the thread is now exiting, and it will return some value. If the count variable is less than 500, then it would print that exec statement back to the main thread. Otherwise, it would return that the count was greater than 500 back to the main thread. So let's try to compile this program. Now you must know that we need to include this flag, which is the -lp thread, to link this thread library with this particular program, and then simply execute this program. So as you can see that the threadfunc started and exited after some time, and in the main thread we got the value from this subthread which was the threadfunc, and then at the very end the main thread exited. Now what if we did not have this particular pthread_join in our code? So if I just change this value to 0, by the way, if you don't know what this is, you can simply create a comment section which will be turned on and off using the values that you put in right over here by using the hash symbol followed up by the if command. So let's dry run this code first. So we do not have any sleep command in the main function. That means that as soon as the threadfunc is executed, the main function would simply exit its execution. So we would not pass the time that is required for this for loop statement to execute. Therefore, no value would be returned to the main function. So if I save this program, recompile this code and rerun this code, you would see that the main thread did not wait for its subthread to complete its execution and exited right away, which resulted in a defunct process. We already know what a defunct process is. This means that a subthread was still executing its execution while the main thread has exited.
Even after the subthread finished its execution, no value was returned to the main thread, or I should say the main function. So that is why we use the pthread join to make sure that the main function exits its execution at the very end. So in this video we're going to talk about deattaching a thread and cancelling a thread. So what do we mean by deattaching a thread? Well, in the previous video we talked about how the pthread join function can be used to obtain the return value from a thread. By default, a thread is joinable. This means that when it terminates, another thread can obtain its return value using the pthread join function. And if a joinable thread is not joined by calling the pthread join function, then the terminated thread becomes a zombie thread. Now what does this zombie thread do? Well, a zombie thread is a brainless thread which is only consuming system resources or system memory and not performing or creating any useful information. So that is why we need to deattach zombie threads from the system resource. For that we have the function which is the pthread underscore deattach. Before moving on to the syntax of this pthread deattach function, remember that the system automatically cleans up the terminated threads, so there is no need of explicitly calling the pthread join to get the return value to stop it from becoming a zombie thread. Anyhow, the syntax of deattaching a thread is as, first of all you need to include the library which is the pthread.h, and then you have this function which has the return type integer pthread underscore deattach, and it takes only one parameter which is the thread itself. So basically you pass in the thread in this parameter as an argument, and then that thread is deattached from the system resources. Upon success it returns 0, and upon some kind of error it returns a positive error number which is also known as error. So that was deattaching a thread. But what is cancelling a thread? So basically there is a function which is the pthread underscore cancel. It also takes in one argument which is the thread itself, where it is used to cancel the execution of a specific thread, or in other words we can say it is used to force terminate the thread. So now to demonstrate the deattach method, we have this very similar code that we used in the previous pthread join function, but the only difference is that we are not returning any value from the subthread which is the thread func. So we are simply calling the pthread deattach function, and the ID is given by the pthread underscore self. So what is happening is that this thread is calling the deattach function on itself. The only way for this process to execute and to terminate is by completing their individual executions and then calling the pthread deattach function on itself. So if I quickly compile this code and execute this program, you can see that I get that the main function has exited, the thread has started, and after some time the thread would also exit. However, we do not have any exit command neither in the main function neither inside the thread, but it exited and removed itself from the memory and stopped itself from becoming a zombie process due to this function which was the pthread underscore deattach. If this function was not used, the thread would have become a zombie thread and would have stayed in the memory until your machine restarted. Now we have another program over here which is to demonstrate the cancel function. So as you can see in the thread, we have created an infinite loop by setting the condition for while loop to 1, and for every execution of the while loop we have put a delay of 1 second, and in the main function we have created a for loop which would count to 9, and then it would call the cancel command on this infinite thread. So if I compile this code and execute it, you would see that both of the threads have executed their execution, and after the main thread counts to 9, it is going to call the cancel command on the thread which is the thread func. See, after the main thread counted to 9, every processing was stopped. So the main point is, if you are working with multiple threads and you do not have the idea of one thread will stop its execution or if it will become an infinite thread, then you want to set a condition, and upon the success of that condition you want to pass on this command which is the thread cancel, or I should say pthread underscore cancel function, so that the thread does not stay in the memory forever and does not consume the memory resources. Anyways, that was thread deattaching and thread cancelling using some functions. Okay, so in this video we are going to talk about the thread synchronization. Now, right off the bat, I'm going to start with a code to explain thread synchronization in a much more clear way. So as you can see that I have this code on my screen, and in this code, the very first thing that I'm doing is that I'm creating a global variable of integer data type. And then let's head inside the main function and see that we are creating two threads. The first thread is known as the T1, the other one is known as the T2. These individual threads are performing some action, we'll go over them in a while, but at the end of this main thread, we are just simply taking the value of the global variable and printing it out to the terminal. from within the main function. So let's head inside the thread 1 and thread 2. So as you can see, inside each individual threads, we are simply creating two variables, one for the loop and one for to store up the value from the global variable. So now as you can see that this loop is about to run for 10,000 iterations. And for each iteration, we're getting the value from the global variable and storing it inside the x variable for thread 1 and y variable for thread 2. And then we are increasing the value of x and y in their each individual threads. And then finally, we are simply updating the value of global variable with x for thread 1 and with y for thread 2. So if we dry run this, the output should be 20,000 every time we execute this code. So I'm just going to save this program, open up my terminal and run this code. So you can see I got the value 20,000, but if I keep on executing this same program again and again, you will see something very weird. As you can see, for the very first two times we got the value 20,000, but after that the output was pretty unpredictable. We got like 15,000, 10,000, 11,000 and then again 10,000. So this was caused due to the synchronization error between multiple threads. So why is this happening? Basically, let me open up my code once more. This part over here, which is to update the global variable and to get the values from the global variable, these three lines on each thread, this can be called as the critical section. Now we have talked about the critical section in the video atomicity. So we're not providing atomic execution to these individual threads, or more precisely to the critical section. So if you want to get the desired result every time we execute this program, we need to include a way to make sure that atomicity has been achieved on this critical section. So how do we do that? So we can achieve atomicity by using Mutex. So what is a Mutex? A Mutex is a type of lock, and the data type for Mutex is pthread_mutex_t. Now to avoid the problems that can occur when multiple threads try to access or modify a shared value, we must use a Mutex. Now Mutex stands for mutual exclusions. As I've already mentioned that we need to ensure atomic access to shared resources. So Mutex is used for exactly that purpose. A Mutex has two states, a locked state and an unlocked state. One key point when using Mutex is that at most one thread may hold a lock on Mutex, and hence only that thread can execute the critical section. And when a thread locks a Mutex, it becomes the owner of that Mutex lock, and only that owner, or I should say only that thread, can unlock the Mutex. So now I have another code right over here, and in this code I'm going to use Mutex to ensure atomicity for the critical section. So as you can see, I still have my global variable, and right beneath it I have created a Mutex, and the command for that is pthread_mutex_t, and then I've put the variable name for Mutex, which is the mtx. And to initialize the Mutex, you need to use this command, which is the pthread_mutex_initializer. Now if we head inside the thread, by the way, the main section of this program is exactly the same as the previous one, so I'm not going to go inside the main section. So as you can see in both of the threads, right before we head inside the critical section, we're actually using the Mutex lock condition. Now the thing with the Mutex lock condition is that it returns 0 upon success and a non-zero value upon some kind of error. Therefore I have stored the return value in this ret variable, and I've used the function pthread_mutex_lock, and inside here I've passed the address of my Mutex, which was mtx. After creating that lock, I can get the value from the global variable and store it inside the variable x. Then I can increase the value of variable x and then update the value of global variable by x. After that is done, I am going to need to unlock the Mutex. So the statement for that is, again I'm using the variable ret and pthread_mutex_unlock, and I'll pass in my Mutex, which was mtx. So that is how I'm making sure that when I'm creating a lock, or when one thread is executing a lock, no other thread can access that particular critical section, making sure that both of these threads do not access the global variable at this exact same time, and create a synchronization to when to access that global variable. So now I'm going to close this program, open up a terminal and compile this program. Now as you can see on your terminal that I got the value 20,000. But I'm going to execute this program a few more times to make sure that our value stays the same. So as you can see, after running it for about 8 or 9 times, I'm still getting the exact same value, which is 20,000, and which is the exact output that we wanted. So We have now created atomicity for that particular critical section by enforcing synchronization upon multiple threads using the mutex. So in this video, we are going to talk about the thread synchronization using condition variables. Now we have already talked about the thread synchronization using mutex, but there was one problem in that particular approach. And that problem is that we do not have the privilege to set the sequence of the thread execution itself. I mean, we can set the lock on the critical section, but we cannot choose which thread needs to be executed first. So when it comes to thread synchronization, we want to be able to choose which thread needs to be executed first. Therefore, we use condition variables. Now, a condition variable allows signaling from one thread to other threads about changes in the state of a shared variable. Now, what do we mean by this? Basically, all of the threads are sharing a specific variable, and then change in that variable notifies all the other threads or a specific one to start its execution. Now, condition variables help to define the sequence of a thread execution. For example, in case of a producer and a consumer thread or a producer and consumer application, we want the producer thread to run first, which means that the producer would produce some kind of data, and then we want the consumer to consume that data for some further execution or to perform some kind of operations on that particular data. So we are going to move to our code right away to better understand what is thread synchronization using condition variable. This whole code consists of two subthreads. One is producer and the other is consumer. The producer is producing data and the consumer is going to work on that data only when it receives the signal that the data has been compiled. By the way, you need to make sure of one thing, that the condition variable are used in conjunction to mutex. You cannot use the condition variable on its own. So the very first thing that we do inside this program is that we create the mutex variable and the condition variable using the following lines. So we know how to create a mutex variable. It's pthread underscore mutex underscore t, which is the data type, followed up by the variable name, which is mymutex, and then we set it equal to pthread underscore mutex underscore initializer. That means we need to initialize that mutex. Similarly, the exact syntax is followed by the condition variable, only the data type changes. So the data type is pthread underscore condition underscore t, followed up by the variable name, which in this case is myconvar. Set it equal to pthread underscore condition cond underscore initializer. And then we are also creating two global variables. One of them is the integer data type, which is the done flag, which would be used to notify the other threads whether the data has been compiled or not. And then we have the buffer array of the character data type, which takes up to 100 bytes in the memory. So before moving into the threads, we are going to go inside the main function. Here you can see that we are simply creating two different threads. One of them is thread A and the other is thread B. And then we are using the pthread join function to wait for the thread A and the thread B to return some kind of value, so that our main thread can only exit after the subthreads have finished their execution. Now that everything is clear, we are going to move inside the thread A. So as you can see, the very first line in thread A and even in the thread B is that thread A has been scheduled first, and respectively we have thread B has been scheduled first. Now what is this? So basically, we are first going to print out to the terminal of which thread has been scheduled to execute first by the kernel. And then we are going to give it a sleep of 1 second. And then, as I've said, the condition variables need to work in conjunction with mutex. Therefore, we are going to put a mutex lock on the critical section. So that is what we are doing over here. We are putting up a condition lock using the mutex variable. And in here, we are simply producing some kind of data and we are storing that in the buffer array. And then we are changing the value of the done flag variable to 1. And after the data has been produced, we are going to use the condition variable to send a signal using the function pthread underscore condition cond underscore signal. And then we are going to pass in the condition variable, which is myconvar. Now what is this condition signal? Now basically, this condition variable works on two different functions. One is the signal and the other is wait. Signal is to notify all the threads that the particular task have been achieved. Now you can start your execution. While the wait command is to tell the threads that we need to wait for some kind of signal from the higher end thread, or maybe in this case, which is the producer thread. After sending that signal, we are unlocking the mutex. So let's go inside the thread B. So we know that we are printing out which thread was scheduled first, and then we are using the mutex lock again. But this time around, since we want this thread B to execute after the thread A, so we are going to check for the done flag. If the done flag is 0, which means the data has not been compiled by the thread A, in that particular case, we are going to use the function pthread underscore condition underscore wait. Now this would tell this particular thread to halt its execution until the condition variable changes its state, and this thread receives a signal to start its execution again. Now the cool thing is we have put a mutex lock, so even if the control changes back to thread A, it won't be able to access that particular critical section. Therefore, this wait function, what this does is that it removes the lock from the variable passed in its second argument. So we are unlocking the mutex lock in this statement and then waiting for some change in this myconvar variable. And upon that change from thread A, what this function is going to do is that it's going to put up a lock once more to this critical section from thread B, and then it's going to perform some action on that critical section. And then at the very end, we are going to manually remove that lock using the function pthreadMutexUnlock. So in this way, we would be able to overwrite the scheduling done by the kernel and produce a sequence of thread execution on our own. So now if I save this program, open up a terminal to compile this program, and then execute it, you can see one thing, that the kernel scheduled the second thread first. That is why we got the output that thread B was scheduled first. But the thread B was the consumer thread. Therefore, it went inside the code, used the wait command, and the control shifted back to thread A. Then thread A started its execution, and then the thread A changed the flag by accessing the critical section and gave a signal to all the subthreads using the variable myconvar. Now thread B caught the signal from thread A and started to execute its critical section after the execution of thread A. And then we were able to print out the data in the buffer, as you can see over here. And after both of these threads executed, the main function also finished its execution and ended the program. So that is how you can create a sequence of thread execution using mutex plus condition variable. So in this video, we are going to talk about the inter-process communication, also known as IPCs. So what is IPC? Well, IPCs are used to send and receive data between processes, or maybe within the same process between multiple threads. Now IPCs are not only used to send and receive data, but they're also used to synchronize between processes. I mean, we have used an IPC to synchronize between processes, which were the mutex and condition variables. Staying to IPCs, there are two types of inter-process communication available in Linux system programming, which are communication-based IPCs or synchronization-based IPCs. The communication-based IPCs are of two types. We have the data transfer-based IPCs, which include the pipes and FIFOs. And then we have the memory sharing based IPCs, which include some kind of shared memory. Now, the other type of IPCs were synchronization based IPCs, which includes semaphores, mutex, and condition variables. We have used mutex and condition variables, and we know that they are used to communicate in between multiple threads of the same process. So in this video, we are going to talk about the pipes for inter-process communication. So what is a pipe? Well, a pipe is a byte stream used for inter-process communication. A pipe, if you imagine a real-world pipe, has two ends, but in Linux, the ends are known as the read end and the write end. I mean, if you look at this diagram over here, you can see a cylinder which is known as a pipe, and it has two ends. One of them is going to be called as the write end and the other one is going to be called as the read end. Now, to perform these reading and writing operations, we need to have some kind of file descriptors, and that is because the pipe creates a temporary file in the memory, and to write to that file you need to use system calls such as the read and write. Now we are familiar with those system calls, and we also know that to use those system calls we need to have some kind of file descriptor. So when we initialize a pipe, the writing end of the pipe gets the file descriptor 1 and the reading end of the pipe gets the file descriptor 0. So let's talk about some features of pipes. Pipes are usually called as the unidirectional communication medium in Linux processes. Now pipes usually have a very limited amount of capacity. Usually it is 64 kilobytes, and a pipe is simply a buffer maintained inside the kernel memory. And sometimes it is also known as a temporary file. But the only difference is that a file would contain an entry in the file system, while the pipe does not create an entry in the file system. Anyhow, when the pipe is full of data, further write call to the pipe will be blocked until the data is removed from the pipe. Now remember, writing to the pipe puts data onto this kernel memory or the buffer in the kernel memory, whereas reading data removes data from this buffer maintained inside the kernel memory. So let's talk about pipe creation. Well, pipes are really easy to create. We need to include the library, which is the unistd.h, and then we have the function integer pipe which takes in a single argument, which is an array of integer data type known as the two file descriptors. Upon success, this returns 0, and upon error, it returns -1. So the last question is, if it is used for inter-process communication, then what are those types of process in which this can communicate? Well, pipes are used to communicate across related processes. Now, what are related processes? Well, parent and child processes, or I should say, if a process creates another child process by using the fork system call, then these two processes are now related to each other. And pipes are used to communicate between such processes which are related to each other. Also, one key point is that after you have executed the fork system call, the child process would inherit all the copies of its parent's file descriptors. So now if you take a look at this program, you can see that I have included the library unistd.h, and in the main function I have created an integer data array of 2 variables and called it fd. And then I have created a buffer array of 50 spaces, and then I've also created a data array of 50 spaces. So I'm going to use the file descriptor from the pipe to write to this buffer array, and then I'm going to read the data into this data array. So now we are going to create a pipe using the pipe function, and we are going to wrap this function into an if statement so that if we get an error, we could exit the program manually. So we're calling the pipe function and we're passing in the file descriptor, which is the integer data array, and we're checking if the return value of this pipe function is -1, then that means that we have encountered an error. And in that case, we are going to prompt the user that there was an error in the pipe, and then we are going to manually exit with this call exit1. If there is no error, the very first thing that we are going to do is that we are going to fill up this buffer array. So for that, we have the function sprintf, and then we are going to pass on our array and then the data that we want to write to this array. And then to store this into the kernel memory, we are going to use the write system call. Now again, I've told you that we would use all the system call that we use for file system for pipes as well. So we are going to use the write system call, pass in the file descriptor, but remember the index would be 1 because the write end of the pipe is on fd1 and the read end is on fd0. So we're going to pass in fd1, and then we're going to pass in the array which is buff, and then we're going to pass in the length of that array using the function string length. Once we have written this data to the pipe, we can now read this data by using the read system call. So we are going to use the read function or the read system call, pass in the file descriptor 0, and then we are going to pass in where to store this data. For that, we are going to use the array data, and then we are going to specify the number of bytes that we want to read from the pipe. First, we are going to read out 5 bytes, and then we are going to read out 5 bytes, and lastly we are going to read out 10 bytes. So if I save this program, compile it using our terminal, and then execute it, we get the following output. So as you can see, the read system call worked perfectly. First we read 5 bytes of data which we got pipe, and then again we read 5 bytes of data and got the string data, and lastly we read 10 bytes of data and got the string example. So that is how you create a simple pipe in the Linux operating system. So now in this code we are going to demonstrate the working of pipe between a parent-child relationship. So in this code we are going to create a parent and a child relationship, and then we are going to use the parent process to send the command line argument to the child using pipes. So in the main function, as you can see, we have created 2 file descriptors and we are calling them pfd because we already know that the file descriptors of the parent are passed on to the child. So that is why we are calling them pfd, so we know that it is the parent's file descriptors. And then we are creating a buffer array, or I should say a character array of 50 bytes. And then we are creating a variable of data type size_t to store the value from the read and the write system call. And then in this if statement, we are trying to create a pipe, and upon some kind of error, we are going to manually exit from this program. If there is no error, then we are going to create a child process using the fork system call, and we are going to put this fork system call into the switch statement. So if the return value from the fork system call was -1, which means that there was some kind of error in creating the child process, so in that case, we are going to manually exit from this program. Otherwise, case 0 stands for the child process, while the default over here stands for the parent process. So let's talk about the child process. So the very first thing that we are going to do inside the child process is that we are first going to close the right end of the pipe. Now, I've already talked about this, that whenever you use pipe, you use them in a unidirectional manner. Now this means that the parent would only have the write end and the child would only have the read end, thus creating a pipe in which data flows from one side to the other side and not bidirectional. So that is why in the child process we are closing the right end of the pipe. And then we are going to create an infinite loop, and in this infinite loop we are going to read the data from the read end of the pipe. using the parent's file descriptor, and we are going to store that into the buffer. But before doing that, we are going to clear the buffer by using the command string copy, and we are going to copy in an empty string inside the buffer. If the return value from the read system call was -1, which means that there was some kind of error reading that file or that pipe, then in that case we are going to exit the program. And if the read system call returned a value of 0, this means that the parent has closed or terminated its processing, or maybe the parent has closed the right end of the pipe. So we are going to print that out and we are going to exit from this for loop. And then what we are going to do is that we are going to print the data that has been received by the child process from the parent process onto the terminal using this printf statement. And then lastly, we are going to close the read end of the pipe because we want to clear up the memory, so we need to remove the parent file descriptor from the memory as well. So we are going to close the read end of the pipe from the child process as well. Now coming back into the main program or the parent process, the very first thing that we are going to do is that in this program we are going to close the read end of the program. Again, we know we are trying to create a unidirectional stream of bytes, so that is why we are going to close the read end of the pipe. And then what we are going to do is that the very first thing is we are going to prompt the user that this is the data that I'm going to be sending to the child process, and we are going to get the data from that list of command line arguments. And to actually send the data, we are going to use the write system call, get the arguments from the argument list and write it to the right end of the pipe. Then we are going to sleep this program or the main program for 2 seconds, and then we are also going to close out the right end of the pipe. And if there was some kind of error while closing the right end of the pipe, we are going to manually exit from the program. After closing the writing end, we are going to prompt the terminal that we have closed the writing end of the pipe using the printf statement. And lastly, we are going to exit from this code. So all in all, what is happening is that a parent process is creating a child process is waiting in an infinite loop to get some value in the right end of the pipe. As soon as the parent writes some data to the right end of the pipe, the child reads it and prints it onto the terminal. The child closes the read end, the parent closes the right end, and the whole process comes to a break. So let's see how this communication works when I execute this program. So as you can see, I have the command for my pipe program, but I need to pass in some kind of command line arguments. So for that I'm going to use something like Linux and hit enter. So as you can see, the parent says that I'm going to send the following data to the child, which is Linux. And as soon as the write command is executed, the data is received in the child process. Then the parent process closes the writing end of the file. As soon as the child notices that the right end of the pipe has been closed, the child prints it to the terminal, stops its execution so that it can also terminate from the memory. So that is how inter-process communication between related processes such as parent and child occur due to pipes.
So in this video, we are going to talk about the IPCs using FIFO. Now the FIFO stands for first in, first out, and FIFO is very similar to a pipe. It is so similar that in fact it is called a named pipe. They almost have the same working, but let's see the principal difference between the pipes and the FIFO. Well, the biggest difference between a pipe and a FIFO is that a FIFO has a name within the file system, and it is opened in the same way as a regular file. Now this would mean that we would use all the function or the system calls we use on a normal file, whereas a pipe does not have a name in the file system. Now a FIFO is used to communicate between unrelated processes. Now what do we mean by this? Consider an example of a client and a server. Both of them are not related to each other as they are operating on entirely different mechanisms. However, pipes are used to send data only between related processes. For example, a parent-child process. Once a FIFO has been opened, we use the same input-output calls as are used with pipes and other files. For example, read, write, close, and much more. Now, as I said that FIFO is very similar to pipe, this means that a FIFO also has a read end and a write end. That is why it gets the name first in first out, because first data written to the right end of FIFO is the first readout from the reading end of FIFO. So let's talk about creating a FIFO. So to create a FIFO, we need to include the header file system/stat.h, and then we have the function whose return type is integer, and the function is mkFIFO, which stands for make FIFO, and it takes in two parameters. One is the path name and the other is the mode. What is this path name and mode? Basically, as I've said that FIFO has a place in the file system, so the path name specifies where you want to create that FIFO file. And then the mode defines the accessing permissions for user groups and others.
Now this function returns 0 on success and returns -1 on error. So as you can see, I have two files, one is the write FIFO and the other is read FIFO. So let's start with the write FIFO. So as you can see, I have included all the libraries that are required for this program to run, and then in the main function, the very first thing that I do is I create a variable to store the file descriptor, and then I use a character variable to make a string of the path, and then I want to store that message in some array. So for that purpose, I'm creating a character array, and then I'm going to use the function make FIFO, and the path name is going to be my FIFO, and for the accessing permissions, I'm going to pass in 0660. Now once the FIFO has been created, you need to open it as you would do with any normal file on your Linux operating system. So for that, I use the open system call to open up the path name myFIFO in the write only mode. Now I want this program to run for an infinite amount of time unless I explicitly give it a sigint, which is the Ctrl+C command, and until it is closed, I want it to keep listening for strings from the user to write it to the file, and I would use the other program, which is the read FIFO, to print that string onto the other process. So that is why I have created this infinite loop. Now I'm prompting the user to put in some string on the terminal, and then to get that input I'm using an fgets function and storing that input into the array which is arr2. And then I'm using the write system call, passing in the file descriptor and the array to write the string from the user into the FIFO. And lastly, when I close this program, I want to close the file descriptor, so for that I'm using the system call close fd. And now if I open up the second program, which is the read FIFO or the read end of the FIFO, in here you can see that I have again created a variable to store the file descriptor, and again I have created a character array, and just like in the right end of the FIFO, I am using a character pointer to get the string of the path name. This time around, I'm going to open up my FIFO in the read-only mode, since in this program I only want to read from this particular FIFO. And then I'm also going to create this an infinite loop, and within this infinite loop, I'm going to read the data from that FIFO and print it onto the screen. So if I save both of these programs, open up my terminal and compile both of these programs, and before I execute this program, I am going to open up a new terminal, and in this terminal, what I'm going to do is that I'm going to head inside that temporary folder which I have passed in to the path name of the FIFO. So cd/tmp. In here I'm going to show all the entries using the ls-al command. So as you can see, we do not have any file name as myFIFO. Coming back to this terminal, I'm going to execute the write FIFO over here. So in one terminal I'm going to run the write end of the FIFO, and in the other terminal I'm going to run the read end of the FIFO. So as you can see, in the right end, it's asking us to write a string. So I'm going to write something like hello Linux and hit enter. Now as soon as I hit enter, if I come back to my read end, I get the output that the user 1 has said hello Linux. I can test it out even more, and the string would be passed in to the other process. So basically we are doing runtime inter-process communication using FIFOs and a file system. Now if I come back to this terminal, in which I have opened up the temporary folder and again show the ls-al command, you would see that this time around I have a myFIFO file in this particular folder. So that is how you perform inter-process communication through FIFOs. So in this video, we are going to talk about message queues in the POSIX. So first of all, what is POSIX? POSIX is nothing but Portable Operating System Interface. So let's get back to message queues. So in Linux operating system, message queues can be used to pass messages between processes, just like we do with pipes and FIFOs. But there is a simple difference. Unlike pipes and FIFOs, which are only byte-oriented communication, the message queues are message-oriented IPCs or inter-process communication. Readers and writers communicate with each other in units of messages. The messages attribute are defined by something called a structure attribute. We will go over that as well. Now the thing in message queues is that you can set a priority to a message. Higher priority messages are queued ahead of low priority messages. So that is something you don't get with pipes and FIFOs. Also, message queue entry is present in the file system, and the path to that file system is /dev/mq, which stands for message queue. So to use message queues, you need to use the following system calls, and these system calls are mqopen, mqclose, mqunlick, mqsend and receive, mqset attribute or get attribute. Now you can already see that these are the normal system calls like open, close, send, receive, but they have the prefix mq for message queues. So let's talk about these message queues. Well, we know that open system call is used to create or open a file. Similarly, mqopen is used to open a message queue. Close is used to close down a message queue. Unlink is used to unlink a message queue from a particular process and ready that queue for deletion when all of the processes who are accessing that message queue have finished their execution. Then we know send is for sending the message and receive is for receiving the message. The only thing that is different is set attribute and get attribute. Now we already mentioned that the type of message that can be sent through message queues is defined in the attribute. So if you want to change that attribute structure, you need to follow this function, which is the set attribute. And if you want to get the attribute of the current message structure, then you would use the function mq_get attribute. So let's simply talk about the opening. So for that we have a function called mqopen, and if you remember in the system calls, when we use the system call open, it would return us a file descriptor. So in message queues we also get a descriptor, but rather than being a file descriptor, we call it the message queue descriptor. So the return value from the message queue open function is a message queue descriptor, and this function takes in two arguments. First is the name that you want to give it to the message queue, and the name should always start with a /. The second is the O flag, which is basically the mode in which you want to open up this file of message queue. And if there is no such message queue already available in the path dev/mq, then you want to create that with the flag ocreate, and then you want to set the accessing mode. So if you want to read the manual for message queues or open call in message queue, you want to type in man, which is for manual 3, and mq_open. This is going to take you to the open system call of message queues. So here you can see that you need to include these libraries for the message queues to work. And also you need to include the linker, which is the -lrt, when you're trying to compile a program with message queues. And then you can see all of the functions, the modes, and the O flags over here. So now let's simply move on to the code. So as you can see on my screen that I have made two programs. One is to send the message and the other is to receive the message. So I'm going to go into the send program first. In here, as you can see, I've included all the libraries that I need to run this program. And then I've created a message queue descriptor and called it queue. Then I'm creating a structure of the data type mq_attribute and calling it attributes ATTRS. Now make sure to use the keyword mq_attribute so that it is a message queue attribute or not some user defined structure. Then I simply have the length of the message stored inside a size variable. Okay, how I want to communicate is that I want to get the argument from the command line arguments, which would be the name of the message queue, and then the next argument would be the actual message. The total number of arguments would be 3. First would be the process name, the second would be the name of the queue, and the third would be the message queue. So I want to make sure that I don't have less than 3 arguments. So that is what I'm doing inside this if statement. And then here is our mqopen system call. So I'm opening the mqopen and getting the name from the first command line argument. If that queue is already present, then I'm only opening it in write only mode. Otherwise, I'm going to create it using the flag ocreate. And for the accessing permissions, I'm going to give it read write permission for users and groups, which would be 0660. And for the attributes, remember, the last parameter of this open or mqopen system call takes in the attributes function. So if you want to go with the default attributes, you must use the null keyword. So in this if statement, I'm checking for errors while creating a queue or while opening up a message queue. Also, we need to make sure that the attributes are also set. So in this if statement, I'm checking whether the attributes are working perfectly or if they're returning some kind of error. So basically, if I call this function, which is the mq_get attribute, and pass in my queue and my attributes variable, and the return value is equal to -1, that would mean that there is some kind of error in the attributes of this particular message queue. So in that case, I'm going to prompt the user that there is some attribute error. So if there is no attribute error, after that, I'm going to access the message queues and print to the screen the total number of messages that can be placed inside the queue and the total size of each message according to the attributes. Then I'm going to change the value of my message length variable using the function string length on the second argument. And this argument is actually the command line argument. Then this if statement is a simple check to make sure that the length of my message is not greater than the length defined inside the attributes. If everything is working perfectly fine, then I'm going to use the system call, which is the mq_send, and I'm going to pass in the name of the queue or the file descriptor of the queue, which in this case is not the file descriptor, rather it is the message queue descriptor, and my message which is placed inside the second index of the command line arguments, and then the length of that command line argument. And lastly, I'm going to pass in 0, which would mean that I have to go with the default attributes. And as you can see, I have wrapped it around the if statement and I have put it equal to -1. Basically, it is checking for some errors in this mq_send command. If there is an error, then I would simply tell the user that there was an error in sending the message. So that was the send part of the message queue. So let's talk about the receiving end. So in here again I've created a message queue descriptor, an attribute structure, a pointer to message, a receive variable that is of the size data type, and in the receiving end I want to specify from which queue I am trying to read. So that is why I won't have 3 arguments, rather I would have 2 command line arguments. So that is what I'm doing in this if statement. And then what I'm doing is that I'm opening up that particular message queue that has been passed inside the command line argument using the mqopen call and storing the message queue descriptor in this variable. And then again checking for errors, checking for attribute errors, and here I need to allocate some memory to the message pointer variable by using the calloc function. If I cannot allocate some memory, then I would print out the error that okay, there was some error in creating memory for the message pointer. And if there are no errors, then I'm going to use the function which is the mq_receive. I'm going to pass in my message queue descriptor, my message pointer to where I want to store the message that I have read, and the maximum size of each message that can be read from the attributes. And for the default setting of the attributes, I'll type in null. If I could not receive any message, then this variable would be equal to -1. Hence, I'll print out that there was an error in receiving the messages. Otherwise, if everything is working perfectly fine, then I'm going to simply print out the message to the terminal using the message pointer. So now I'm going to use the terminal to compile both of these programs. Make sure to include the linker library which is the LRT. So now as you can see, I have opened up 2 terminals on my screen, and in one of the terminals I'm going to run the sender side, and in the other terminal I'm going to run the receiving side. Now I need to put in the name of the message queue, so /. Remember, for the name of the message queue you always need to start with a /, and I'm going to call this message queue the bus. I can start my receiving end right now, and for the sending end I'm going to type in my message which is going to be Linux, and as soon as I press enter, you can see that the message was received on the receiving end. And on the sending side, remember the code part where we were printing out the message attributes, or in particular the total number of messages that can be placed inside this queue, which is 10, and the maximum size of each message, which is 8192 bytes. So that is how you perform inter-process communication using message queues in Linux operating system. So in this video, we are going to talk about shared memory when it comes to POSIX IPCs. So the idea here is that we identify a memory location based upon a particular key, and we define how many bytes we want that memory location to be allocated for a particular input or output, or maybe read and write call. So as you can see that I have this code in front of my screen. What I'm going to do is that I'm going to consume a memory location for a particular amount of bytes, and then I'm going to write something within that memory location. And then I would use the other program, which would be the reader program, to read data from that particular memory location using the key value. To use shared memory, you need to include this header file, which is the system/shm.h. So in this code, the very first thing that we're doing is that we're creating a void pointer and we're calling it the shared memory. This would be the address of our shared memory. And then we're creating a buffer array of character data type. This would be used to get the input from the user and print it onto the memory. And in the reader program, it would be used to read the data from the memory location and to print it to the terminal for the user to see. And then we are creating an integer data type and we're calling it shared memory ID. Now to get this memory ID, we need to use the function which is shm_get. Now this shm_get function takes in 3 arguments. The very first argument is the key value. So we are manually typecasting this integer value into the key_t data type, and for the second argument, it is the number of bytes that you want to consume. So I am putting in 1024 bytes. So when you are trying to get that memory location, if it does not exist or if the memory is not shared yet, you want to create that shared memory location using the accessing modes, which would be in this case 0666, which means that read-write mode for user, groups and others. And then I'm going to include a pipe symbol and type in the command ipc_create. So basically, if I do not have that shared memory with this particular key, it would be created. Then I'm simply printing out the key value from this variable onto the terminal. Now to get the address from that particular key, you need to use the function shmat. You need to pass on the ID which we got from the shmget function, and then you're going to pass in null and 0. This would basically mean that we want to go with the default options of this function, which is shmat. So now we are simply printing out the value that we got from the function shmat to the terminal, which is the address of the shared memory. Then we want to read some data from the user from within the terminal. So I'm prompting the user in this line and reading the data with this function, which is the read. And we are simply storing that input in the buffer array that we created over here. And lastly, what I want to do is that I want to copy all the elements inside the buffer array into the address of the shared memory location. And then I'm simply prompting the user that this was the data that you have written to the particular memory address. So now if I open up my reader program, you can see that I'm simply creating another SHM ID and getting the same memory location using the same key value and using the same number of bytes and accessing it using the mode 0666, which would be created if it is not already shared. Then again, I'm simply printing out the key value of the shared memory location onto the terminal and getting the address of that shared memory location using the function shmmat like we did in the writer program. Then all that is left to do is that we want to read the data from that particular shared memory. And in this statement, we're simply printing out to which memory address the process is attached to. And then finally, to print the data from the memory onto the terminal, we're simply using the printf function, and we're saying that the data read from the shared memory is, and then we're simply typecasting the values from that particular memory address, which is stored inside this shared memory variable, into a character data type and printing it onto the terminal. So now if I compile my code, make sure to include the linker file, which is the -lrt. And now I can execute the writer program first. So it is saying that the key of the shared memory is this, the process attached to that particular shared memory is this. And now I can simply write my message over here. Let's say I want to say something like Linux. And now I can read this particular message in the other process, which was the reader process. So I'm going to execute that program now. So as you can see that the key of the shared memory is the same as the one we had in the writer program. And this time around, the process attached to that particular shared memory is this. And the data read from that shared memory is the same which we have given to the writer program. So that is how you use shared memory for inter-process communications. So the last topic in POSIX that we want to address is semaphore. Now semaphores allows processes and threads to synchronize access to shared resources. I mean, we have talked about the race condition and we have talked about how processes can access the same shared resource at the same time, which would result in an unpredictable output. So we want to avoid that. Now we know to avoid that thing, we want that shared process or that critical section to be executed in an atomic manner. Therefore, semaphores are used to execute the critical section, which could be a different process or the same process but different thread, in an atomic manner. Now semaphores are located in the path /dev/shm. By the way, if you want to open up the manual page of semaphore, then you would have to type in the terminal man --7 sem_overview. This would open up the manual page for semaphores. So as you can see, a semaphore is an integer whose value is never allowed to fall below 0. Two operations can be performed on semaphores: increment the semaphore value by 1 and decrement the semaphore value by 1. And if the value of the semaphore is currently 0, then a semWait operation will block until the value becomes greater than 0. So now as you can see that I have this code in front of my screen, which is going to help us run a critical section in an atomic manner. So to use this code or to use semaphores in general, you need to include the header file, which is semaphore.h. To create a semaphore, you need to use the data type sem_t and then followed up by the name that you want to give to the semaphore variable. So in this case, I am simply calling it mutex, as we know that mutex is used for locking the critical section and unlocking the critical section, just to make it easier to understand. So in the main function, I am simply initiating the semaphore using the sem_init function, and I am passing in the variable for semaphore that I have created, which is mutex. And then I am creating two threads, T1 and T2, which would be the subthreads of this whole program. Now as you can see, for the creation of both of these threads, I am using the function pthread_create, and the function that I am passing within these threads is this one right over here. We are going to head inside this function in a little while. So after the creation of the first thread, I am sleeping the main program for 2 seconds, and then again I am creating another thread, which is T2, and again I am passing in the function thread. Lastly, I want my main thread or the main program to exit after the threads have successfully executed their whole functionality. So that is why I'm using the function pthreadjoin. And at the end of your main program, you want to make sure to destroy the semaphore, otherwise it would just keep on consuming the memory. So inside this void thread function, I'm simply using the function which is sem_wait to create a mutex log kind of situation. And once a thread is inside this particular statement, it is going to print out that okay, I have entered into the critical section. And just to demonstrate this semaphore, I have only used a sleep condition in my critical section. And after I am done with my critical section, I want that thread to print out that okay, now I'm exiting this critical section and I want to unlock that mutex log. But since it's semaphore, you want to use the function sem_post. Basically, sem_wait and sem_post work exactly the same way a mutex lock and mutex unlock work. So now if I compile this program, you need to make sure that you include the libraries lpthread and the library lrt. Before executing, I'm going to dry run this program if there was no atomic way of running the critical section. So what would happen is that both of these threads would access the critical section and print out entered, and then both of these threads would sleep for 4 seconds and print out just exiting and just exiting. But let's see what is the output after putting a semaphore lock on the critical section. So one of my thread entered the critical section and after 4 seconds it exited. Now the other thread entered the critical section and after 4 seconds it exited. So we can say that the critical section was accessed by both of these threads in an atomic manner. So that is how semaphores work to achieve atomicity when it comes to critical sections. We have talked about the users and groups in the Linux operating system. So let's talk about the files that contain that information. The information about usernames, access users, passwords, user IDs and much more stuff. So the very first file is the password file. To access that file, you need to type in cat followed up by /etc/passwd. Now as you can see on the terminal, now this password file is a colon separated file that contains the following information. We have the username, encrypted password, user ID number, user group ID number, full name of the user, user home directory and the login shell. And then after that we have a file that contains information about the user groups. Now to access that file, type in cat followed up by /etc/group and hit enter. Now you can see a list of all the processes or all the programs and services installed in your Linux operating system. And then at the very right of each row, you can see the name of the group that owns that particular file or service. And in the start of this course, we have talked about a shadow password file. Now the link to the shadow password file is /etc/shadow. But if I try to access it with the cat command and hit enter, you would see that the access got denied. That is because only privileged processes can access this shadow file. And if I want to access it within my terminal, I need to convert this terminal to a privileged process by running a sudo command inside it. I can either go with sudo space -i or I can simply use sudo space the cat command followed up by the path which is etc and then shadow. Now this file is very different from the password file that we opened recently because this only contains the name of the files or the name of the services and then a very weird encrypted ASCII2 code which is actually the password and the user ID. So that was accessing users and groups in the Linux operating system. So now let's talk about the time functions present in the C programming language for system programming in Linux. Now one thing you must know that there are various amount of libraries that include a time function within them. So you can opt out to choose any library that you want and you can even choose any method that you want for time functions. There are two kind of times available. The first time is known as the real time, which is the actual time of the system, while the second time is known as the process time, which is the time required by the process to finish its execution. However, we cannot use any library to calculate the process time of a process. That is because we need to use the real time from when the process starts its execution to the time when the process ends its execution to calculate the process time. So if we open up our terminal to create a new file, we'll simply call this file processtime.c, and inside this file, we are going to include the library which is the time.h along with the library stdio, which is the standard input-output library, create our main function body, and then we are also going to create another void function and we're going to call it function time. In this function, we are going to prompt the user by typing in a printf statement that the process has started. Then we are also going to say something like press any key to stop the execution of the process. Now we need to make this process run for an infinite amount of time. So for that we can use a for loop without any conditions. So we put in the for keyword and then we simply put 2 semicolons in its parentheses and then carry on with the body of the for loop. And since we have said to the user that he needs to press any key to stop the execution of the process, therefore we are going to use a function which is the get character inside an if statement. And if we get any character from the user, we are simply going to break away from this for loop and exit our process. But before exiting our process, we are going to prompt the user that the function has exited. And then we are going to head inside our main function. And in this main function, we are going to create a variable of the data type clock_t. And then to initialize the clock, we need to set this variable which is t equal to clock function. After we have started the clock, we can call the function which was function time. And when we come out of that function, what we are going to do is that we are going to change the value placed inside the variable t. And then we would have to do a step to manually typecast this variable by using the command double time taken by function is equals to double parenthesis and then t, which is the variable name, divided by clocks per second. Now this variable clocks per second is also included in the library time.h. And then at the very end of this program, we can simply prompt the user about the time taken by the process. And then you're going to exit this code, open up a new terminal, and compile this code using the command gcc, followed up by the name of the source file, which in our case is processtime.c, and then -o, and then the object file, which will be process time. And then you can execute this code by typing in the command ./process time. Now as you can see on the terminal that it says that process has started and to press any key to stop the execution of the process. So if I press any key on my keyboard and hit enter, so it prompts us that the time it took for the process to complete its execution was 0.000249. So that was time functions in the C programming language used for system programming in Linux.